All right. It's 4 o'clock. So that means that we are good to go. I see a couple of people here already. It's great. The good thing about having a conference virtually is that people can catch up later because it's obviously naturally recorded. Uh, what I'm going to do is I'm going to open the conference with a short introduction to what the community is, what different platforms we are using, what the objectives are, and so on. I will also be speaking about why this community was started, what's kind of the roadmap, uh, basically of the next year for this community. Uh, and once that's done, like that's the introductory meta part of the conference. I won't take more than 5-10 minutes. After that, we're going to have Akshay, who's going to be stepping in for Amit, who was unfortunately not well today, who's going to be talking about EMS automation tools and how they use those to build PCB Kingdom. Then we have Anul, who's going to be showing us how to design and render beautiful PCBs using a combination of KiCad, FreeCAD, and Blender. And then we're going to have Jitin, who's going to be talking about how to make scientific instruments using Python, which I'm very excited for because that's something that I don't know a lot about. So I'm very curious to learn that. So yeah, so that's the general agenda for today. So we are expected to go from 4 o'clock, which is now, to around 7 p.m. And tomorrow we'll have the same timings. We'll start at 4 p.m. and go up to 7 p.m. And we have, I think, 4 different talks tomorrow as well. All right, so let's start. What is this Makerville.io? Makerville.io has a rich history. I was using that as a company name for some contracting work for some time. It was also the name that me and Rituparna Matkar and Rohit Gupta and a couple of others used to do our interactive installations once upon a time. So it has a lot of names. It has a lot of meanings over the years, but now it's reached that point in its life where it knows what it's good at and it's going to stick to that. But Makerville is basically a forum for Indian makers, right? So first of all, who am I? So I am Anuj Deshpande. I currently work as a hardware engineer for a company called Balena. Some of you must have used Balena and that product called Balena Etcher to flash SD cards or USB drives with the operating system. So yeah, Balena is that plus like 10 different things. I work on the hardware team there. I work on making their single board computer called Fin and a couple of other things. But yeah, that's my day job. That's what I do from Mondays to Fridays. Uh, Before this, what I used to do was I was an engineer, a software engineer at semiconductor companies for 4 years. Two out of those were at a company called Espressif, which is everyone's favorite microcontroller, the ESP8266 and ESP32. So there I used to work on connected stuff like connected microcontrollers, Wi-Fi, Bluetooth, BLE, those kind of things, AWS, IoT. Yeah, those were kind of the things that I did there for a while. Uh, Before that, I was part of a team of makers here in Pune who crowdfunded a BLE development board fairly successfully. That was a very nice learning experience, and that's where my hardware journey kind of started. Because before that, I was just doing software development for hardware. After that, I was more involved in the other aspects of hardware as well. Other than that, in my free time, me and a couple of friends make interactive installations, which are like I think of them as creative outputs for some of the stuff that I don't get to use at work, but I still like to explore. So that's me. I also am a huge fan of barbecues. The next question that I'm going to now, that introduction out of the way, that gives you an idea of who I am. Now let's talk about why you're here, the community, right? Like why start a community for Indian makers. So a while ago, there was a community called Indian Hardware Startup Network. It was a discourse forum initially, and it was amazing because it was super rich in terms of content. It had a lot of stuff. For some reasons, Mahesh, who was the person who started that, I believe, decided to migrate that to Facebook groups. And that's okay, right? Platform is just the means to an end. But Facebook groups probably didn't work out very well, and that community is not as active as I would like it to be. Plus, Facebook has a bunch of issues in itself, and I personally hate them a lot. So that's like I miss IHSN basically. It's one of the reasons that I did this, started Makerville. So the other thing is like it's a no-brainer because if you're working on four different skill sets in your career, right? Let's say uh, interacting with people who have similar skill sets, talking about projects, collaborating with them, bouncing ideas off each other. It's just a net zero sum, non-zero sum game, right? Like it just means that everyone is going to benefit from it. That's the whole point of this community. There's no downside to it, right? So the only downside that I think that can happen is like people who are maintaining the community are burnt out by it. But so far, I don't have that yet. But hopefully, I build enough automation tools to allow me to take breaks. But I think this is a no-brainer to build something like this. There's a lot of us here in India, and it just makes sense to have a place where we have the hive mind basically to talk about ideas, to post links, to criticize, critique, whatever, right? So that's the idea for that. The other thing that's part of the Makerville forum is that it's specific to India. Now, I'll try and explain why that matters. If this was software, that would not have made sense because software is pretty independent of everything, right? It's the same here, it's the same in Africa, it's going to be the same in Australia, whatever. But hardware is actually quite regional. Uh, for example, if you look at how you design a product, it's also dependent on what you have available, right? For example, I was talking to a colleague of mine, and acrylic is actually very expensive to fabricate and to buy in Greece. It was, I think, almost 3 or 4 times as expensive as what I have here in Pune, right? So if I want to make a prototype out of something out of acrylic, it's a pretty no-brainer thing. But someone like him would think twice before, you know, actually making a quick prototype because it's obviously more expensive. So the availability of materials and stuff really impacts the way. Really impacts the way that you design something. The other thing is we have reasonably low cost labor here. So even those processes that uh, come into the foray of manufacturing and production, everything, those also get impacted by that. So we don't optimize for some things and we over optimize for other things, which is not the same in other places where there's probably a lot more automation, like Europe, for example. Yeah, availability also influences design. For example, we don't have warehouses for a lot of things here in India. For example, I wish Mauser or Digi or someone had a proper warehouse in Bangalore or something, but I don't believe they do. That's why everything that we build is usually shipped from abroad, everything that we order from these sites. So then we have to resort to smaller sellers who have only specific chips because obviously they are smaller sellers. And then that sometimes does influence your design. Like you would use something that's available easily to build a prototype as opposed to something that is the right choice. So again, this is a regional thing. The other thing that I wanted to build this is because I've been very fortunate enough to have passive mentors, right? What that means is that those I don't walk up to them and tell them that okay, from tomorrow you're mentoring me on something, but these are people that I talk and interact with and learn something about them, and then that influences things that I do in my life, in my professional life, right? And this has been the case before with remote working. Now I'm a remote worker now. It's been the case with me deciding to get into hardware and a bunch of other things. Like if I really think about it, I could probably write down a dozen different things that were influenced by my interactions with other hardware folks. And I think I'm going to be needing obviously more of that going forward in the future, but I think that's something that everyone needs. So that's why there needs to be a place where this can be facilitated. Plus, I'm a huge fan of India. I really like our country. Besides, like the governments come and go, but the idea of India is pretty amazing, and I think we could be doing a lot more on the hardware front than what we are doing right now. Like we have a lot more potential than what is the current state. Of course, we have a lot of good things already, but there's a lot of work that needs to be done. This is my small contribution on that particular journey. Okay, so what exactly is Makerville? Makerville is a forum. So if you go to makerville.io, you will see an actual forum. You'll have long form posts, discussions, quick reference posts. Unfortunately, we also have a Telegram group, which not exactly unfortunately, but unfortunately, it's more popular than the forum itself. The problem I have with that is Telegram groups are not indexable by Google or DuckDuckGo or whatever. Right? So even if we discuss something which is a very interesting discussion, someone new is not going to have, like, it's not going to be very easy for them to find out about that discussion and learn from it. Right? So that's it's an unfortunate part that's happened, but I'm rolling with that. The other thing is this conference itself. So this is the first edition and this is the first talk, but hopefully the following talks will be a more accurate representation of what this conference is going to be about. The Telegram group, as I mentioned. So if you wanted to join that, it initially started at something where I could plan the conference. But yeah, it's become a lot more. There's a lot more people who are active on that group and so on and so forth. So this is an example of a post on the forum, which is like I've pointed to a link which I'm maintaining on GitHub, which has a list of all the e-commerce stores that are there in India, right? And this is the kind of stuff that I want to be doing more of, like resources that help someone when they're quickly looking for something, right? In their professional careers. Like if I'm looking for manufacturers of a particular type of PCB, if I'm looking for acrylic laser cutters in my area, those kind of things, like those kind of things are going to be seen a lot more on here. This is another example of what kind of posts are there on the forum. This is, so you can't buy a Prusa Mini in India which is manufactured here because it's only manufactured in one place. So then this post talks about my experience of importing it from abroad and the different charges that I faced and timeline that it took and everything else. Right. Okay, so this is my plan for 2021, right? So reduce friction. So for example, I realized after starting the community and the forum that the Telegram group is a lot more active than the forum itself, right? And that's okay. That's not necessarily a bad thing, but I kind of need to make that work in a different way. So what I'm going to be working on is creating a Telegram bot that syncs content from the Telegram group to the Makerville.io website. I'm going to also start a newsletter, which is just going to be discussions from that week and other interesting links that people have posted, and that's just curated and just sent out as an email. Start documenting projects. I already started this on Makerville, but I'm going to start using Makerville as a project log kind of thing. I'm not super sure that this is going to work out because there are better platforms like Hackaday for that, but I'm going to give that a shot, and it's going to be an experiment of mine anyways. I also started this thing called shared inventory management. Basically, I don't know what's a good name for that, but if you go to inventory.makerville.io, there's a part keeper instance that's running. Thanks Sitaram for helping me host that. But basically, that is something that I want to use is to create a library. So if I don't need a Raspberry Pi 4 right now, but someone needs it, they can borrow it from me and return it back. This is again risky and involves a lot of non-technical factors like trust and like people actually returning stuff. So this is going to be like a slow experimental thing, and I'm going to see how it goes. Anul actually initiated this project, and we already are seeing some great stuff happening on that front. But we have a traveling hacker box now. If you go to thp.makerville.io, you should see the all the different places that it's been to. And if you go to the forum, you should see all the different stuff that's already there in the hacker box. The other thing that I want to start is something along the low-level programming kind of stuff, because that's something that I always want to work on for myself. It's the book club, basically. So there are some classic books that are there. The C programming language is one, structure and interpretation of computer programs. I was recently reading Linkers and Loaders by John Levin, which is an amazing book. So these kind of books, I mean, anyone who's interested in like a book club, please let me know, because this is something that I want to really start with this particular community. So yeah, that's basically it. This is an introduction of what is happening with Makerville.io as the community, as the group of people or whatever. And a community is only as good as the people in it. And so far, I have been extremely lucky. Everyone has been very helpful and has been working for the cause, and that's great. And I hope that we continue the momentum. I'm not super excited about increasing the number of members, so I'm not going to be pushing down some marketing kind of stuff about the community or any other meta stuff. I'm just happy that I will be like working on making the experience for whoever is here already better. Like that's the only goal that I have for 2021. So hopefully next year when you come back here for this conference, I would have worked on some of those projects that I just mentioned. And with that, what I'm going to do is I'm going to take a quick 30-second break. And then after the break, Akshay is going to join us, and he's going to be talking to us about how he and Amit have been building. Amit, who couldn't be here today because he was... Oh, actually, Amit might come join us, actually. But basically, their journey on building PCB Kingdom. So I'll just introduce a quick break for everyone here. Go grab water or something. Hey guys, can you hear me all right? Amit,
yeah, we can hear you.
Awesome. Okay, so we are now on the first proper talk. We have a bunch of people who are commenting. So Amit and Akshay, if you want to keep an eye out, there's a comment section here on the right that you can click, and that will show you the YouTube comments, right? So feel free to take a look and answer questions or whatever. But
I can manage the comments, Akshay. You go with the talk.
Okay.
Yeah.
No, perfect.
Okay, so yeah, so guys, this is Amit Kocheria and Akshay Sharma, who are building PCB Kingdom for some months now, and we are going to be hearing a lot about how their journey and the kind of stuff that they're building. Right, guys, over to you.
So yeah, so I think an interesting topic to talk about: EMS automation challenges, or in simpler words, how not to drive your EMS provider crazy. So that's what we have been working on from last 1.5 years on trying to find ways not to drive him crazy. So let's get to the first set of slides. So the quick intro to both of us. I've been working as a hardware designer who dabbles in a little bit of software whenever required, but now my favorite part, but whenever needed, I dabble through it. I work on digital circuits, industrial designs, power, electronics, as well as some automotive designs. In the past, I've had experience of working as a hardware designer for the Arduino. Had opportunity to set up their India production plant, and now here I am, few years after that, trying to help everybody with their hardware challenges and making it their life easier to take their designs from design to production. I'll let Amit give an intro on himself.
Hi guys. So yeah, I'm the opposite. So I'm a software engineer who actually dabbles in hardware. I know enough to be dangerous, but I couldn't design good hardware if my life depended on it. But I was tech lead for the 96 boards effort at Lenaro. And one of the things we found there is there's a lot of great ideas. People have good designs, but then if you want to do prototyping at small prototype volumes, it's extremely hard. Similarly, it just takes too long to go from your designs all the way to production. You've got to talk to multiple different vendors. You've got to get quotes, and then you have to. I mean, the entire process is essentially very outdated, I feel. And I thought we could do better than that, and so that's why Akshay and I we met at Siddesh, who's probably here, at his makerspace, and we decided we could do better, and so that's how we started PCB Kingdom. By training, I'm professionally I'm a Linux kernel developer. I've hacked on Zephyr RTOSes and so on and so forth. Carry on, Akshay.
So yeah, so let's go to the first question that we will have in ourselves. What is EMS? We've just been using this word all over the place. So I mean, Wikipedia gives us a very tough definition. Let me just simplify it for you and put it in very simple pictorial form. Whenever you have to manufacture any electronic board, you need a PCB, you need components. So you're just going to get your PCB manufactured, you're going to get components procured from different vendors, you're just going to get them all put together into a nice looking board. That's what you're going to take home and work and make something beautiful. So let's go to the first most interesting part of it. It has three major parts: the PCB manufacturing, then you have to procure the components, and then you have to get them all put together. So let's start off from the PCB manufacturing side of it. I know designing PCBs, Anul is going to come back and teach us or give us some nice heads up how to use KiCad to be more professional and more proficient. But let's look at how the things are going to be manufactured. Then let's look at design with his help. So what's basically a PCB? A circuit board which you see, green, blue, yellow, whichever color it comes down in. Simply it's just a circuit designed in an electronic CAD software. It generates a bunch of files called Gerber files. Those files are used by manufacturers, and you get a circuit board coming out of it. So from here, let's look at it. Sounds pretty simple. It's just a bunch of files going down to a board. What's complicated? What is the challenge? Why are we trying to solve this? Sounds right. You are pretty correct on this. But let's see why the issue. Now we got about 10 to 20 very known softwares out there which are used for designing. Take it from KiCad, Eagle, Altium, Proteus, OrCAD. There are like about 20, 30 very famous ones. Each one follows a different rule. So the biggest issue right there is the files which are being generated, the Gerber files, they have their own naming conventions. This standard started way back in 1979, and there are some softwares who are still following the oldest form of this oldest form of the guidelines. The latest version was still in 2014. This keeps evolving every few years as the consortium comes to a better understanding. Then there are players like Mentor Graphics who come with proprietary Gerber formats as well. So having a unique software which is going to read through all these together and be able to give you something easy to use is a challenge in itself. So let me just give you a slight sneak peek at how the naming convention of these files could really go down to. I'll just pull up an Excel sheet which will show this out. Just a second. Okay. The Excel sheet. Okay. Just give me 1 second. Yeah. Okay. So as some of you might be knowing, you have PCBs from 2 layers, 4 layers, 6 layers, 8 layers. So just going from all the layer names here, the first 2 columns is signifying some layer names. And over here, I have names of softwares and the file names which are generated from there. They are not similar at all. Every software has its own naming convention, has its own way of putting it out there. Just a second, my computer just decided to act a little funny. Give me 1 second, please. Apologies for this. Okay, then we'll bring it back up. Yeah, so Eagle will generate a different file format, KiCad will generate a different file format. Okay. So every layer gets a different name. We'll come back to the layers and the naming one more time, but just for this a sneak peek towards it, every software has a different name, and every software generates a different extension to it. So it gets really complicated at trying to automate this and picking out which software generated this and how do you handle these files. So going away from this, let's look at what these layers are. So in a simple, a PCB is nothing but a stack up going from copper layers and some form of dielectric layers in the middle. So I've given 2 examples here, a 2-layer board and a 8-layer board. Over here, you have multiple layers. The most important ones are the coppers, the top copper, bottom copper. Then you have the green layer, which is sitting on top, which is the color of the board. Over here, I've chosen a green, for example. You can have any color of your choice. You have a silk screen, which is nothing but your namings, branding, any kind of information which you want the user to be looking at while using the PCB. And then you have a paste layer, which is used for production. So the naming convention could be just as simple as solder paste top.gbr, whereas for an 8 layer it will be the same, and you just keep adding for every layer possible. The naming conventions are something that's the first step towards trying to identify if these files are working for us or not. Let me go to what comes next. Next is something called a stack up. Each PCB layer is made up of some form of dielectric, some form of copper. So it's going to be a copper, a dielectric, a copper, a dielectric, a copper, a dielectric, copper, a dielectric. You can go up to 20, 30 layers. So every layer will have its own properties. Every material will have its own properties. The choices are infinite. There are about 20 different types of materials you could choose as your dielectrics. You can define the dielectric constant you're looking for. You can define the thickness of PCB. So in simple words, you have about 10 parameters to choose from to define how a PCB should really look like. So to make it simpler for anyone to use, we always suggest using standard stackups. Every manufacturer has its own capabilities. He may be good at 2 layers, 4 layers, 6 layers, 8 layers. He may be using a predefined thicknesses. So whenever somebody needs a PCB manufactured cheaply and fast, we always suggest using a standard stacker. But the biggest question comes, will this work in every possible case? The answer is no. When you have a very strong RF-based design where you need every layer to be of a given dielectric so that your antenna performance is tuned accordingly, you may want to change each and every dielectric constant so that you get your antenna tuned to your needs. So over there, different stackups will be required. People have been changing these annotations, the file names a lot. It's not easy for any software to really pick up which file really belongs to which layer. The next problem which comes down to is people putting excess data for us. The biggest example will be you have the Gerber data put out there. Right next to it, you have a small table showing what is the stackup required for the PCB. As soon as a automated system goes in to read these files, it looks at, oh, I was trying to find the dimension of this PCB. It should be only having some data from X to Y. But because of the table, you get a really different size of the PCB detected. So this creates a lot of problem in automation. That's what we are trying to solve in different ways. People are still using very old Gerber naming conventions, which have been outdated by at least 10 years. So in simple words, if you follow these guidelines, your PCBs generally will work quick and fast. Anything, Amit, you want to add here?
No, I think we're good.
Okay, so let's go to the second part. Once the PCBs are manufactured, let's go towards getting the components from different places. So in every folder, you have a very simple file for any design, a file called bomb.xls, or it's just an Excel file with the bill of material that just tells you which component goes where on that PCB. What are the resistors, capacitors, ICs, different connectors which are going to be on there. It's just specified in this file. We have to go then buy. How tough can this be now? The question is, it gets even more complicated because every resistor, every capacitor has a unique part. It's called the manufacturer part number. So let's look at a bomb. Let's start from a simple example, how a bomb would look like, and what do we care about. This is a very simple bomb which anybody in any form of electronics working with it would have made at some point of time. So it starts off with, oh, I got this part called C1, C3 of this quantity. That's the value I want. That's the package I want. It sounds good. That's what we have done for all of them. But let's look at it a little closer. This bomb is not that easy to decipher. It is a mystery in itself. So we have no tolerances, no wattage, there are values missing, and there are packages missing. So I cannot identify if this person wanted a resistor of, let's say, 100 ohms here of 0805 package, but he did not tell me if he wanted 1%, 5%, or a 0.5%. So it gets, now the question comes, if you're going to a local shop, he will ask you this question. When we are trying to automate something like this, who do we keep asking this question to? Can this computer really find this out himself? The answer is no. That's why we are looking for a manufacturer part number. Then the second part over here, the person just mentions he needs a connector. It needs 6 pins. I'm like, sure, here you go. You have 6 options. Which one do you want to choose? If we do this for a bomb which has 100 parts, and if we keep asking them for questions, for these are your 100 options for each part, it's going to take him about 4 days to just answer, oh, this is my final bill of material. This cannot be a solution for scale up of manufacturing if you're trying to do this in large volumes, a product a week, or any R&D lab who's trying to dabble into this at higher speeds. So having this information being read automatically through different systems is very important. Let's look at it from what a reply do we get from an automated system. Out of a list of 27, we are only able to find two through the automated system. The other 25 parts need clarification. There is something or the other which is missing. So in the next, let's look at how this should really look like. This is the same bill of material. I have just added a column called MPN, a manufacturer part number. So this is a unique number for each and every component you want to choose. So it may take you a bit of time in making the choice of what you really need, but when you send your files down to the manufacturing, you're going to get exactly what you want. Chances of errors reduce, chances of conversation reduce, you are saving time, cost, effort, and you're going to get more and more reliable in your design. So moving from having a very perfect BOM, let's look at what do we really need to do to get your components sourcing right. You need to be clear on what your manufacturer part number is. Make sure you don't put unique, every shop and all will put their own SKU on it. I want to call this resistor of 100 ohms, let's say PCBK 123. When I'm going to try and source it in the market, it's not going to be so easy for me to find. It has a unique number. We should keep using that. Every component should have a proper designator, which is going to be looked at in another file called pick and place file, which is used for assembly. We'll talk about that later. But all this, the designator also has to be mapped so that we know you have mentioned something called as C1, and that's what the value corresponds to. This is the manufacturer part number. This is C1. We are able to match them and able to use them. Don'ts. You really don't want to be using a part in your bill of material which is out of stock. As soon as you punch these files for manufacturing, you're going to get a reply, oh, your thing cannot be manufactured. Here are your PCBs. You find yourself with this component. And as soon as you get to know this, you have to go back and go change the part. So this is, I mean, you want to be not doing this, not using parts which have really high lead times. That is, it's going to take really long for it to come from factory to the assembler, so that it gets, you're waiting on this one part for the whole board to be soldered, because you either run all or you don't run anything. Because when you have a pick and place machine running to place all your 200 components on a given board, you can't make it run for one component. It's a process which has to be run once. You do it for the whole batch or you don't do it. So a lot of times we get delays because of these kind of parts getting stuck from manufacturer, customs, or wherever it be. Now let's moving from getting components. Now it's time to, we have already got the PCB. We know what not to do there. We know how not to order components. Now, once we have all these parts together, let's get them all together to make that one fancy looking soldered board. I like, okay, now this is easy. Now we have already taken part of the major hurdles. We already had the right parts. We already got the PCB. We feel we got it right. So now somebody just has to match the following things together and give it to us. So that's what PCB assembly is all about. You get the PCBs, you get the components, you have another file called the XY file, which is nothing but a placement file. It tells us which component is going to be sitting at which place. For example, this particular chip has to be placed at this place. So it's going to be given an XY coordinate in this particular file. Maybe his name is X1. X1 sitting at coordinate number 10, 10. It's going to be placed out there through a high-speed pick and place machine. Okay, sounds good. Where is the challenge? The challenge still comes in. I'll hold on and show you what the problem comes at. So right now, just to let you make life easy for the assembler, let's just give him the placement file properly. Let's give him a proper file name. Let's give him designator names like X1, R1, R2, all this in one place. Perfect. Every user is going to be asking us for two things. Can you handle a small volume rapidly for me? The answer is, if you go to every manufacturer, maybe yes, maybe no. Because running a batch of 5 is equal effort as running a batch of 2000. It's the same effort putting all the things, loading into a machine, pick and place, and getting it done. You're asking, can you give me a standardized pricing formula? Maybe yes, maybe no. So these are things which I'll talk about how we have handled a little later. So now let's go to an interesting part, where, how, and how you can really trouble your assembler. You felt you had everything right. You got your right piece of components. You got your right piece of PCB together. Now it's time to assemble. We're like, this is the easy part. Now let's look at how we really trouble our assemblers. Okay, if you see these images out here, I bought the right parts, what the customer told me. I got the right PCB, but the package is incorrect. What do I really solder here? That's what the assembler is going to be asking. Over here, we have the footprint mismatch again. Over here, we have a connector which has an incorrect footprint. What do I really do? Over here, it's another package mismatch. Over here, we have a switch. It's got 5 legs, but there are only 3 holes. What do I do with the rest? Isn't this really troubling the assembler's life? So moving on to another sort of way to trouble him, we say, okay, I am giving you a BOM. I'm giving you parts. Let's look at it. So after looking at the BOM and the parts, we find out, okay, according to the customer, we have 4 parts which are supposed to be there, which do not match. And we're like, okay, he might have just made a tiny mistake. Let's just see what logically fits. We realize, oh, these 2 guys are small enough, they can fit here. This guy's big enough, he might be able to fit here. You're like, okay. But then getting a conversation with the customer, we realize he wanted something else. He wanted the big tantalum capacitors here and the smaller ones here. So having your thinking you had your BOM right, thinking you had your PCB right, you still have opportunity for making things fail. Now comes the biggest horror for the assembler, the mystery of the connectors. The customer sends a packet of connectors and makes the assembler guess what to solder where. Even let's say there was a 4-pin connector needed. He has packed one 4-pin connector which looks like this, another which looks like this. What does the poor assembler do? He will have to keep having communication with you and asking for questions and really figuring out what you need where. So if you're not able to give good data, it's always going to add time. So when we are trying to prototype fast, we need to be more accurate on our data and make somebody else's life easier for soldering. When you're hand soldering 5 boards, it's fair. You can do whatever you feel like. But when you're asking somebody else to solder, make sure you have given him enough information so he does not keep coming back to you for help. Let's look at some of more mysteries of the connectors. Now, the footprint does not match in the first image here. That's fair. Okay. In the next one, we got the footprint right, but we did not get the diameter of the holes right. Okay. In the next one, we got the diameter and the footprint right, but we did not give enough spacing for the connector. So isn't this going to trouble the poor assembler again? So moving on from here, once the assembler really figures out what not to solder for you, he's going to be, oh, there is still more problems. Now comes, according to the BOM, we have a location called S1, which you can see here. The BOM says there is a switch here. The assembler goes, sure, here is my switch, I'm supposed to solder it. He's like, where the hell do I really solder this? Then he figures out, oh, the customer needed a terminal block. He's providing incorrect information. So this is one of the last stages in your production, and you're figuring out you have an error. You have lost enormous amount of time. Now let's look at another kind of a problem where there are some devices have orientation. LEDs only work in a given direction. Anode to cathode, cathode to anode. The way you're going to configure it, you make your choice. Over here, the designer was very nice. He was kind. He made a really nice dot over here that this is going to be my negative side. That's where you solder. But he still made one error. He did not look at another layer, which is called the paste layer. So when the PCB actually got manufactured, the dot did not show up because this got taken away from the paste layer. Now we have 200 LEDs with no names and no direction. What am I supposed to solder and how? And if you're doing this for 1,000 boards, 200 into 1,000, you're at 200,000 LEDs. You do not know which direction you need to solder at. So moving on from here, another set of direction issues. Over here you see there are 3 capacitors which are marked. These came up without any form of direction. And reverse capacitor can blow your complete circuit out. So having directions for each and every part mentioned in some form or the other, either on the PCB or in a document separately, should be there to make somebody else's life easier. Picking up a footprint and making a quick PCB, that's fair. But can somebody else use your work to bring it to life? So moving on to another kind of what humans think and what machine thinks out here. Over here, you have another interesting problem. You have a component called XT3. It's a crystal. It's got 4 legs. 2 are ground, 2 are the terminals for the crystal. Logically, we can see it's a rectangle. I can flip it, put it again, it'll still work. Pin number 1 and 3 are interchangeable. 2 and 4 are interchangeable. Now, you can understand this, I can understand this, but can the machine really understand if this is how you're supposed to be putting it through? So adding a simple dot right next to it and giving orientation can really help the manufacturer out. So let's just move out some general notes about assembly. Everyone, and I mean by everyone, the most experienced, also have a tendency to make error. So do not trust your own data. Keep rechecking it. Make sure you give the right data. Assembly is the highest stake of the whole product, and it's the last step. So if a fault is figured out in assembly, you have already lost about 2 to 3 weeks in your time. So if you're going to have something manufactured in 3 weeks, you have an issue at week 2, and if you have to go back to box 0, you're adding 3 more weeks to your whole timeline. So make sure your assembly data is always right. So moving from what the data of all 3 phases, PCBs, the components, and moving on to what your assembly needs, we go on to what really a turnkey situation in our present scenario is. So let's look at it, what we are in this, what happens in India right now. One has to dabble through 3 processes separately themselves. They have to go to PCB manufacturing, component sourcing, and PCB assembly, which is handled at different vendors at different places. So you have to be sure of how logistics works with each vendor. It is going to require collection of data of spreadsheets from all these vendors put together and trying to find pricing, putting together timelines, and trying to understand how the whole project planning is going to be. The quotations in itself, since it's a human effort, you're going to give your file, somebody's going to keep asking you these questions because you've given them incorrect data. At the end of it, you're going to get a quote. This may take even up to several days. And I've seen it takes even up to weeks. After that, coming in for certain parts have really high lead times. Let me give you a present example. The STM32F0s and STM32F1s, which are like very go-to microcontrollers right now, are sitting at 17 weeks timelines. It starts at it used to be a $1 chip. Presently, it is a $7 chip. Can you really identify this? Can you do this? So we need to be very careful about this. And since prototyping is always slow and expensive, we need to be careful with what we are trying to offer to the assembler. Now let's look at how we at PCB Kingdom have tried to redesign this and rethink and what can make somebody else's life easier. We have gone through these problems tons of time. So so what we really are, we are a logistics company and a manufacturing company where we understand your complete end-to-end logistics for electronic manufacturing. We offer 24/7 quotations with under a minute. If your files are right, we'll give you a quote right there, including for your components. That if a particular part is going to be available for stock or not, and if you have mistakes in your bill of material, we will point it out right there, right then. So it allows you to not hassle through customs and import duties. We offer INR billing with GST compliance. We offer it in 2 weeks. Presently, COVID has hit the logistics a little. We are running a little slower. We are at 3 weeks for now. For any design going from prototype, from your design to a fully assembled board. We have very predictable timelines. We have highly optimized pipelines. We do automatic order routing for supply chain disruptions. Example, for the STM32, we have been able to identify different sources. So from there, we also are MOQ independent. That means we handle anything from as small as 5 PCBs going up to a few thousand boards if you really need that manufactured in the same 3-week timeline. So to handle this, we do it a little differently. We have real-time APIs for gathering component data, which gives us the live stock, the minimum order quantity for any part, and the pricing brackets they are sitting at. What is the right price to buy it at, and what lead time a component is throwing right away. So as soon as a file is uploaded, we will be able to tell you if your part is available, something can be manufactured or cannot be. Once you have agreed that this is what you want to manufacture, you place an order. We use an internal tool called BOM Optimizer. That's the magic of the game. It goes down to everybody where how to make this cheap, reliable, how to optimize pricing. At the end of it, it decides what are the number of orders for a day. We are able to load all the orders in all our vendors at one shot. We have to do is end of the day go to each one and just make the payment, and all orders are placed in one shot, which is optimizing somebody else's work. We don't have to dabble through talking to 10-20 people and getting, oh, this part is available, not available. We handle it automatically. This enables us to give faster deliveries at all volumes. So we are maintaining some common part lists that will enable us to be much more cost efficient and reduce procurement times. So this is something on a common part list, which is going to be live on our website in some time soon. Let's go to a small demo, and then I'll talk about what our further goals are. I'll speed the demo up. I am running short on time, so I'll do that. Okay. So let's just go quickly to the website. So let's hope the demo gods are on my side today and we have nothing going wrong against us. So I already have a zip file created, which is, let me just show you what the zip file should be really containing. It should be having your BOM, it should have your Gerber files, and it should have your placement files, which is for assembly, this is for procuring component, this is for your PCB. So we just go ahead, upload a file. I have a set of demo folders. So let's look at something called a Jelly 2. It's a simple project. Let me just look at what's inside the folder. So Jelly 2 has set of Gerbers. Okay, for some reason I have an empty file. Okay, I just uploaded the Gerber. I'll show you what's the content of the file. So it's just going around calculating what the size of a PCB is, what are your components you really need, how many layers you are, then it'll just give you options of what you need to be doing. By the time this runs through, I will upload another file on another parallel. That's my third tab and the fourth tab. So over here, I'm going to have some missing files. So I've already created something which does not have a few files. And on the third one, I'll upload something which has a few errors in the BOM. So just to show you what the site is really capable of. And so that's my third file which I'm uploading parallelly, which has incorrect BOMs. Okay, so let's look at the first one. The code is already here. The website says, cool, your design can actually be processed. But maybe you just want to wash out. You got 3 warnings. That is, you have 2 parts which are DNP. And you have a component which is probably going to be running out of stock. But we'll still be able to manufacture for the available quantity. So let's go to the next. Proceed. The quotation does not belong to you. Okay, let me just log in again and re-upload. Demo bot had to come in, so sure. So let me just, okay, I do not have a valid ID. Let me get another instance. Give me a moment, please. So probably I'll just logged in from too many users on that particular instance of Chrome. I'll just upload the file again here. Let's not worry about it. So sample orders, demo. We were uploading Jelly 2 and right there. So the file just went up for upload. Yeah. It's processing. Give it like about 30 seconds. Let's just wait for it this time. And in parallel, let's just wait. Then let's upload the second one the next time. Yeah. Okay, it's processed. It gives the same error again because those particular parts are giving the error. You go to proceed. It gives you how your PCB really looks like. It was a nice, fancy looking jellyfish somebody had designed. You have all the quantities out there. There are no other extra hidden costs. You can just choose out which one you really like. You like white? Go ahead, go for it. You like immersion gold? Go for it. So it just gives you the PCB you really want to look at. So this particular, it's an open source design, which I'm just using as my example. I just choose, okay, I want to manufacture 50. And if you look at it, the pricing just keeps dropping as you go and higher in volume, which is fair. You want to say something to us, feel free, write us, hit proceed. It'll just ask you to log in, hit pay, you're done. It gives you option, oh, I just need to hit pay. That's my cost for 50 pieces. I got my taxes added. That's my address, and I'm done. So moving on from here, let me just upload one of the 2 error ones, and so that I can have time for my questions. So let's just look at something which has a incorrect BOM. Bill of material, I have put in dummy data. As in, I've just put in random words in the middle of the manufacturing part number. And let's see what does the website do with it. So here, so I had put in place of MPNs, dummy data, random data, these kind of words in the bill of material, and it just does not let me go and take the order right there. He's like, go fix these files. I can't buy this. I can't make it. So if I can't make it, I can't buy it. So it just throws you the error right there. It also has, there are some files which are not missing, but paste files are not your concern files at certain point. So it allows you to go with warnings, and it had 1 DNP and a few errors. So that's kind of my demo here, which kind of shows you what the site can really do. I can get into a lot more different things what the site can do a little later. I use it as my testing tool as well if my production files are ready for production or not. I just keep uploading the file. Oh, all my parts are there. I'm getting no MPN errors. I'm not getting any Gerber errors. My files are good to go. That's how I use it there. Then it goes to what we really are intending to do. So what we are, our ultimate goal is reduce the reliance on the Eastern vendors, get more and more competitive on pricing, and be as speedy as possible. PCB manufacturing and assembly is already done in India, so we are not buying anything from outside and bringing it in and just pushing it out with our own labeling on it. It's all done here. Component sourcing is our present bottleneck. Our Indian customs are our biggest friends because we do not know when something can be stuck. Presently, we have a customs a parcel stuck from last 10 days. We're waiting. We'll get it sometime soon. So we are rolling out to the world very soon. We are supporting the Western customers or any other worldwide customers through INR billing, but we'll support all other currencies very soon. And the biggest and the most important part, which we feel is going to help the complete manufacturing community, is through us helping our vendors, which is to optimize their manufacturing capabilities, help them with better QA services, automating QA for them, minimizing time spent in doing back and forths with minuscule things like, oh, your part is not being found, we are not able to source this. All this is being done. We are also bringing in a replacement part list, which is going to make life easier for everyone to use. You have a standard part list, you want 100K register. Oh, I should just use this because it's available with them. So that's a kind of thing coming in. The common part list and the replacement part list are these kind of structures. We will be able to suggest parts in some time as well. We are using some standard open source projects which are doing this, and we are contributing in them as well. So that's kind of it on the PCB Kingdom side. I am looking at anyone who has any question I need to be answering. Please go for it.
I think while you were speaking, Amit has been taking care of the questions. Yeah, there are a couple of questions. Like, for example, do you have to handle importing of components? And as Amit replied, yeah. So that's not something that I have to worry about. But yeah, I think that's a feature I personally like a lot, because I hate replying to emails from anyone, including DHL and Mauser.
So one of the things Akshay has already referred to this. I mean, we are extremely interested in improving the overall EMS system in India, and what we are trying to do is come up with templates essentially to make sure that your order gets fulfilled correctly the first time without too many back and forth with your EMS vendors. And so if there are any ideas on how we can simplify your lives, and Git push does not qualify, Anuj. I think we're happy to talk to you about that. I mean, you've already heard about some of our plans. If there's anything else you have for us, please let us know. We are actively working on this, and I don't want to use cliches, but essentially we want to. I might have to use it. Basically, I want to be able to manufacture all this locally in India without having to depend on our Eastern vendors for a lot of these things. At the moment, we feel that we are price competitive, but the thing that is a challenge in India is turnaround times. So that's one of the things we found. I mean, if you send it to somebody in JLC PCB or all PCB, they can get any kind of PCB out to you. I mean, their turnaround times are literally 2 to 3 days, and that I think is going to be the big struggle. But as we work with these vendors and we improve our own processes, we believe we can get to those efficiencies as well. So we are working with our local partners about that.
I mean, I just like the last Anul's comment, no ETOK on it. I mean, yeah, if there is a note on any PCB, we are not putting our own symbols and logos on it. But yeah, so we know the pain. We completely sympathize with you.
All right. I guess that's it. I mean, guys, just go to pcbkingdom.com, and if you have any questions, I've already also included the Twitter handles for both of these guys. So feel free to ping them on Twitter as much as you want. And I guess I'm going to now call on Anul for the next talk, which should actually have been the talk before this because that talks about designing PCBs. So we are doing a tenet kind of thing where we're flipping time or something, but now we know how to manufacture PCBs. Now we're going to find out more about how to design and render beautiful PCBs. So thanks, Amit, and thanks, Akshay. This was actually helpful. And honestly, like after I used PCB Kingdom a couple of weeks ago, I was very certain that I need to get you guys on here because this is pretty slick. Like it's I'm very excited about the other things that you're working on and adding here, but this is good stuff, and all the best to you guys.
Thank you.
Thanks, Anuj, for hosting this, and thank you, everyone.
Yeah, we'll see you guys in the comments.
Yeah, behind.
Okay, so next up we have Anul. I am waiting on him to join, but till then we'll take a quick. Oh, okay. So yes.
Yeah.
Hey Anul,
Hi.
can you hear me? Okay. Yeah.
Well, I'm here.
Yes. All right. So Anul is one of those guys who is like a gem for the community because he's active on a lot of fronts. He's always sharing good stuff, and I'm really glad that he's been very actively involved in the Makerville community because, yeah, that like those are the kind of people that we want in the community that makes us keep coming back for more and more. So Anul's done a series similar to this on Hackaday. I think you can find videos about this there as well. I think that those are longer duration than this, Anul. Is that right?
Yeah, they're about an hour and a half or probably more. There's also a course over there that goes.
Yeah. Yeah, of course, yeah. But anyways, I'll stop talking and I'll let Anul take over. So Anul, if you want to share your screen, just hit the share screen button at the bottom. All right.
Okay, you want to wait for a short break or should we jump right in?
I think we can pick up.
Either one. Okay.
Yeah.
Right.
So I'm going to just remove myself and leave it up to you. Thanks, Anil.
Okay, but it might help me if you can moderate this and see if there's any questions I'm missing. Because I might
I'll keep on reading now.
Please. Okay, so for those who don't know me, this is my day job, Limitronics. This is where it's a family business where we design and manufacture custom test equipment. So it's more of an R&D activity. We don't have regular production. And the stuff that we build is used to certify products like home appliances, for example, or other industrial products for safety performance. So when you want to get an ISI mark or a UL mark or a let's say CIE mark or any one of those international standards, you need that equipment that will test your product for certain tests. So that's what we do in it since about 40 years, I guess. Can't remember. So anyway, that's my day job. And about a decade or so more ago, I got back into active tinkering. So I used to tinker a lot when I was a kid, when I was in school and early college. And then because of day job, I had to kind of give it up in the middle. And about a decade back, I started this with a friend of mine. It's a loosely knit group of people who love and enjoy making open source hardware. So my teammates are based in DC and Boston and a couple of other places around the world. and we come together, build projects, and essentially with the intention of having fun. So we don't really have a proper business model in terms of making money, but we were doing this in order to, let's say, make our hobby self-sustaining, because we figured out buying a 3D printer, making a CNC machine, buying an oscilloscope costs a lot of money. And if I have to pay for it from my day job, it's going to cut a big hole in my pocket. So we thought of using our hobby to pay for itself, and we're pretty successful at that. So uh, we are not in it so much for making money as in making enough money to sustain our hobby. So I think there's a difference in that. We aren't being too greedy about how much we want, just enough so that we can kind of buy all the cool things that everyone wants nowadays. Besides that, I am been part of the Makers Asylum. So any of you who have heard of that, I've been there since inception, sort of a co-founder since about 2015. The asylum is now moved to Goa, unfortunately, which means I'm stuck in Mumbai without them. And but I'm still on as a let's say mentoring capacity for them and try to help out with whatever projects they have. So these are the things I do. The other thing I do is write for Hackaday. For those of you who haven't heard, maybe I'll have a short presentation tomorrow on the whole Hackaday ecosystem, because there's a lot more besides just the blog. But this is where I write about the stuff that you people are doing. So if you look for the blog post that I've written, this is something that went out this week about a chain, sorry, a clock that is made using drag chains. It's a pretty amazing piece of engineering that has been done by Ekagra. So this is what kind of keeps me busy 24/7. My day job and my 3 fun jobs at OILM, Makers Asylum, and Hackaday. And then, of course, I try to help out as many people as I can with, let's say, tutorials and training sessions and stuff like that. All right, so a while ago, I kind of did a last minute poll to see whether you folks are more interested in looking at the KiCad part or the Blender part, and I don't think there has been much of a consensus. So I'll just kind of wing it from here. I don't have anything prepared. I don't have slides ready, so I'm going to do things live. But let me share my screen. All right, so just to drive in the point that Akshay and Amit were talking about, this is the first prototype of a badge that we were designing for the Open Hardware Summit in 2013. And I goofed up on a couple of footprints, the SD card and the level translator. And fortunately, I mean, this was fabricated at Seed Studio for us, and their engineers were enough of hackers to be able to solder magnet wire and actually put on the wrong components on this PCB just to make sure it works. Yeah. And then we went on with certain with fixing all the errors and going through a second iteration, a third iteration. I think the 4th time around was the final product, which arrived at the conference one day before it was opened up. So it was quite a challenge. So yeah, I mean, it's really very easy to mess things up with electronic design. And no matter how often you do it, you still mess it up. So it's not like you have to be highly experienced to make a mess. So having said that, I'm going to go with a short Blinky badge on KiCad if that's okay, Anuj. Do you think that works? Because
Yeah,
at this point,
that works.
I'd like to introduce something about best practices to make things for people like PCB Kingdom, to make things easy for them. And I've been doing open hardware for a decade now. The other day we were having a conversation on the Telegram group about what constitutes an open hardware project, and different people have different definitions for it. But uh, it helps to know exactly what is required in terms of uh, resources or things that you need to disclose when you say you have an open source project. So I thought, let me show the process that has worked for me. What are the things that you need to have? What are the stuff that you need to do to make a good open source project? So actually, this is a typical project that I'm working on. So let me just do something like modify. So here's a typical structure for a GitHub repository that contains everything for a project called Halo. And there are some files and folders that I consider as being extremely important when it comes to claiming that your product is or your project is open source. So if it's a hardware, there's usually three things to it: the electronics or the PCB part, the hardware part, maybe the enclosure or some stuff that's more mechanically oriented. And if it has a microprocessor or something like that, then you probably already also have firmware or code like that. So I obviously have an Arduino directory for my project because that's where the code is stored. The other important folder I like to have or add is what's known as data. This is where I dump in all of the data sheets, even if I already use them in some other projects. The reason being, if someone forks and clones my repo, they have all of the data sheets available with them for the important parts that I use. Might not be for each and every part or component. Like there's no point in adding a data sheet for a resistor or a capacitor. But some of the things, like if I use a specific diode, then having a data sheet handy is really useful. So if I'm referring to some circuit in this project, then it helps to have a schematic of that. For example, I use some part of the Arduino Nano here, probably just to get the SPI connector numbering right. So I just put a reference to that here. So a data sheets folder is, I think, kind of pretty important to add in your overall project hierarchy. Then I have a couple of fabricate folders. This is where the mechanical design is put in, the FreeCAD files, and derived from those FreeCAD files whatever I need to do the laser cutting and the 3D printing. So for 3D printing, there will be STL files. For laser cutting, there will be SVG files. So not DXF, because that's kind of proprietary. So I prefer not having DXF unless it is absolutely. So that's your mechanical design. These are the files I sent for production to JLC PCB. So it contains whatever JLC PCB needs: the position file, the Gerber, and the Bob. Those are the three things that any, let's say, a PCB fab might need. I also like to add an images folder that contains, while we are working on the project, we store all of our pictures over here. So we kind of remember what we're doing and how things have progressed. So taking a pictorial documentation of your project helps someone because a picture might speak 1,000 words. So one look at a picture and someone might immediately understand how the wiring is supposed to be or how the attachment is supposed to be. There's a couple of KiCad folders that contain different versions of my KiCad design. So as you can see, this one has evolved through 3 versions, V1, V2, V3. And importantly, the license. So the README file would have a link to the license. This one we actually haven't yet completed the project, which is why I haven't added stuff like licensing and all, even though it is still on GitHub and is still open. You can still grab it and do what you want with it. But we're still working to iron out some errors in version 3. The other thing is, in your KiCad repository, you need to also have all of the resources that are needed to duplicate your project, which means not using KiCad's built-in library. I always create project-specific libraries, which you can see. For those who already know how KiCad works, you can notice the halo.pretty folder that contains all of the PCB modules. There's also a .lib. Here it is. So that's the library for the project. And finally, the 3D packages for each of the components. So LEDs, capacitors, pin headers, all of them put in one particular folder. So basically what this means is someone can just take a copy of this folder and run it on their machine and expect it to open up without any errors. There are no missing libraries, there's nothing that's not available, and so on. Nothing is referenced to the local system. Everything is a part of this folder structure over here. So that makes sure that things don't get broken. I have designs from, let's say, 5, 6, 8 years back, which I can still open up without any errors popping up, except a few minor ones for certain symbols in power. But those old KiCad designs still open up without any issue after 7, 8 years. So that's one of the advantages of trying to follow this system of including everything within your repository and kind of segregating it into electronics, mechanical, and code, and then subdividing it to have all of the necessary requirements in terms of libraries and footprints available. The other thing I like to do with KiCad folders is, and this is important, is to have a PDF of your schematic and all the different layers of your circuit board. Now, the reason this helps is if someone is just browsing through your project, let's say on GitHub, and wants to have a quick look at the schematic to see if that's really what they would like to, let's say, download or clone. It helps to have a PDF representation of all of your layers and your schematics available, because otherwise the only way is to download it all, open up KiCad, and then check out if the project is something that interests you. So there's a PDF for things like this, the schematic, but there's also things like the bottom copper layer and the front silk layer, for example, and so on. So one quick look at this and you know exactly what's going on, even though this is not really what was considered as this isn't enough to make it known as open source. I've seen a lot of projects where people just release PDF files or put an SVG or an image file of the schematic and say, well, it's open source. I released the circuit diagram, but it doesn't work that way. That isn't what open source is about. And to help with the PDF and to go along with it, I also had a couple of renders of my layout. So that additionally helps anyone who's looking at this to quickly understand what's going on with this circuit board. So there's a couple of different views, front, top, isometric, and so on. So people get to know what this whole project is about without even leaving GitHub, because GitHub can render images, it can render PDF. So you can quickly check out these things before you decide to download the whole big repo. So that's renders, and yeah, usually that's the whole bunch of stuff that I like to include. And then obviously the final production output. Let's say you have a folder that's going to contain all of your global files. There will also be the position file over here, and somewhere in the main folder will be the BOM file. And as Amit and Akshay mentioned, the most important part is the supplier part number, or the MPN. Once you have this, your item is uniquely and completely identified. So you don't have to worry about any other parameter like what is its footprint or stuff like that. Having the supplier or the manufacturer part number makes it completely identified. So make sure you have that in your BOM folder. So that's what a typical folder structure looks like. And getting here requires a few tricks and tips. It doesn't happen automatically. So let's start off a new project in KiCad. So here's what happens. You start a new project in KiCad. It populates with blank schematic and PCB files. And your first step is to create a schematic. Get that started. You just here. Usually the first thing you do is set up your sheet, populate all of this, revision, title, company, date, and so on. Get that filled out. And add paths here. So let's quickly add paths here. Alright, I hope it doesn't crap out on me. I should have paid attention to the errors I got. Library and all. Battery. Get this. Resistor. The 3 volts there, but only the resistor. LED. Two of them. Let's run it up quickly. Alright, so that's your path. That's annotate them. So they have them numbered. That values. Your 32. Alright, so that's your first let's say PCB. ERC check that here's nothing wrong with this. And if you now look at library references, so here are the three parts on my board. The current mouse is crapping out. I'm using mouse battery. Okay, anyway, so the battery comes from a library called device. The LED comes from the same library, and the resistor comes from the same library. So that's the current library. And if I were to make this into a Git repo, and someone else were to download this, and if by chance they didn't have this same library, or if by some stroke of unfortunate I'm going to switch off my mouse. Let's go with my trackpad. For split kill it and try to what is this? Alright, so if the person at the other end doesn't have the same library, or for example, he has the device library. There's the device library. There's the LED. If by chance their symbol is reversed, for example, then we'll end up opening this schematic with the turned around like this. So that's going to break the whole circuit. So one way of avoiding that is to make sure your project references to a local library that is stored within your project folder itself. So it doesn't come from a global library. If you go to manage symbol libraries, you notice KiCad offers two options to use either global libs or project specific libraries. And as of now, with version 5 point wherever we are right now, it's not really easy to archive schematic libraries. It's much easier to do that with the PCB, but not with schematic. But one easy workaround I found is when you exit this and you go back to your project folder, you'll notice a cache library that it builds up. and this can be used as a project-specific library. I usually like to actually copy and make a rename it to Blinky symbol. So I have this library which is within my project folder, and it's a local library. I can then go back to my schematic. I can add this library as a project specific library. So let me add symbols and okay. And what I can now do finally is go to tools. Go to tools, library references, and here change the current or existing library references to the new one. So I can open up called Blinky Symbols. That is, here's the battery. So that's the first one. So I replaced the symbol by referencing it to the local library instead of the global library. Do the same for the second one. The LEDs. Change it from the device library to the Blinky symbol library. Choose LED. And finally the third one, change the resistor from devices and replace it with resistor in Blinky. Okay. And we now have symbols that have a library reference that is local to the folder or the project that you're working on, and it's not tied into a global library. So if I were now to get rid of the global devices library, for example, my mouse is really coming out. Okay, so I removed the device, save this, close it, start it again. And I still have these symbols because they are coming from this library. Let me get to the before I do this, let me add back device. Okay, I think I'll shut off my mouse and keep my track. I'll add back device. Okay. I'll refer the battery symbol back to device. Okay, so what I have now is the LEDs and resistors as a reference to my local library, but the battery reference to a global library. And if I now get rid of Device. Save this, close it, and hopefully if I started, I should get a missing symbol. Or no, because there is also the cache library that it is falling back on. So if I were to delete the cache library, it would show up as a missing component over here. And that's one of the things. Sometimes with, let's say, a Git repo, if you've added the keyword cache as a git ignore item, you might not have your cache library uploaded on your Git repository, although it might exist locally. So while things work for you, it might not work for someone else who is downloading your repo. Which is why it makes sense to make a copy of your cache as a separate symbols library and use that to call out these symbols away. So that's one part of how you can make sure your schematic isn't messed up. Let's also quickly assign footprints to this so we can make a circuit board and just 3 or 4 parts. So I hope it's picking up battery. So battery. Keystone. That's battery LED. You can just use a 2-volt EMS. So just 2-volt. Okay, so I have footprints assigned. I can save. Okay. Then start PCB new. The netlist. I'm still doing things the old way, although with the new version you don't even need to do the netlist and stuff like that. I will generate netlist file. So let me go back to schematic netlist. Yes, netlist. Okay, here goes. So for some reason, I'm having trouble with my mouse as well as my trackpad. Maybe because my touch screen is goofed up at this point. Yeah. Okay. Anyway, so with PCB new, it's much easier. We have the archive footprints option, so you can just excuse my keyboard is stuck by mouse. So archive footprints just lets you create a new library, which you can call it pretty much the same name as your project and save it, and make it a local library, not global. Click OK. Once you do that, you will notice in your project folder you have a folder that contains your footprints. So like I said, it's much easier to create an archive in PCB new compared to eSchema or schematic. It's going to be difficult for me to do anything unless I can get my screen fixed. All right. So after this, the rest of the stuff is straightforward. You draw the tracks, you draw the outline, you generate the Gerbers, and you're pretty much done. You need to position files. So those steps are already well documented at a lot of places. So I won't kind of go back and forth over them. But I thought these tips on how you can create a self-contained project was important to pass on to everyone, especially for those who are really keen on doing open source work, because this makes sure that you can always achieve the requirements of open source. Let's say. Okay. With this, maybe I can now show quickly a little bit of Blender. How good are we on time, Anuj?
We still have around 20 minutes.
Okay, all right. So because my mouse is crapping out, I have a crazy
Will
feeling.
it be better with Blender?
Yeah. So let me try that. I'm guessing this is a system-wide problem, but anyway, let me see if I can.
Uh,
I
do you
will
think
have
you're
to just log off my computer and log in again, I guess. It might take a couple of minutes to do that, but let me just get Blender started and see how things go here.
I mean, if you have too many applications open, maybe you can try.
I should probably get rid of KiCad. Yeah. And I need this. Probably don't need Telegram at the moment. Get rid of the whole of KiCad. Okay, clean enough. All right, so this is Blender, and if this is your first introduction to Blender, I I can warn you that it gets pretty, let's say, confusing because the user interface is so kind of crowded. I have been trying to learn Blender for about 5, 6 years now, maybe more. And every time I would come here and look at it, and I would look at this cube and try to move it, nothing would happen. I'd try doing my mouse, the left click would do this, the right click, nothing would happen. And after about 30 seconds, I just quit and let it up. But sometime early this year, I got really interested in how I can make really nice looking, let's say, renders of uh, circuit boards using Blender. Let me see if I can show you a quick. So something like this. This is something that's really early, but it gets better as I start doing things with it. For example, you can get to yeah, something like this looks kind of pretty neat. You can add lots of detail to it. You can notice there's values printed on the capacitor, both the capacitor, the resistor, the bands. The IC has the 80 tiny part number on it, and so on. There's a part number on the voltage regulator as well. Now, these are things that doesn't happen in KiCad. With KiCad, you get an 8-pin DIP, for example, or you get just a generic capacitor or a resistor model, but it doesn't have any of these details like bands or markings, stuff like that. And that happens in most of it happens in KiCad, really, not even in Blender. And that's probably a topic for another day. But one way of achieving that is to take a standard model that you might have from a KiCad 3D library, like a 8-pin DIP, for example. Open it up in KiCad and grab logos from Atmel or whoever else, add it to the device and save it as a new model. It's a bit involved in the beginning, but as you keep doing it, you obviously build up a library of parts. So it becomes easier as you keep this get more and more. But in the end, you can get some really nice looking outputs from a render. Uh, why would you want to do that? A lot depends on. For me, it mattered because I just wanted to learn Blender. But if you're building a project and you still don't have a working prototype, but you still like to get word out, nice looking Blender obviously helps to get eyeballs. Maybe you want to add stuff in documentation, for example. So it helps over there as well. Sometimes a KiCad image might not help as much as a nice Blender render. So with that said, let me see if I can quickly get started with Blender. Since I don't use Blender every day, I'm going to refer to Notes because this is not for the faint-hearted. And I don't want to do something. All right, so a little bit of introduction to how a Blender works. On the left is the toolbar that lets you manipulate objects. So there's like you can select objects, or you can move them around, rotate them around, scale them, transform them, and so on. So depending on what you choose, when you choose move, you get the arrow axis, and you can grab on them and move the object. And if you do control, it snaps, for example. You can do it with the other axis. And same thing with rotate, you get three circles, so you can rotate along green axis or red axis, or if you take the white one, you can spin it in an arbitrary angle. And you'll notice the information appears over here. They call it the sidebar, I guess. So there is a particular Blender name for this part, which is up here. And transform lets you scale things in a particular axis or along all three axes. Right? That's if you want to move around, you need to press the middle mouse button, and that lets you rotate or orbit around your object. Or go further. Let me see if I can get screen keys for. Okay, so hopefully. Okay, so I hope you can see this little block here that shows you what keys I'm pressing as I keep it. So that's orbit. Uh, so now a standard scene contains a couple of elements already preloaded. The cube is standard with any new file. Usually the first thing a person does in Blender is get delete this cube, but for the moment let's just leave it here. Then there is this the camera, and then there's the light. These are the three main elements, and then you start adding more stuff. You add more camera positions, more lights, and background, and stuff like that. So for a moment, let's just delete the cube and see if we can import a circuit board over here. So file, import. It doesn't accept a lot of the standard CAD format, so you can't import step file, for example, but you can get WRL, which conveniently is what KiCad can export as. So let's see if we can get a. Meanwhile, any questions?
No, we had a couple of comments about things that people didn't realize that they should be doing with the project. So there's more comments more than questions.
Okay.
Appreciative comments.
All right. Okay, so that's your circuit board. Let me delete. Delete that and do it again because I missed telling you an important part. So when you go to import WRL and you select a file, and before you do it, there are two transform directions that are, let's say, default. We need to change them to match what you expect it to look like. So for Blender, Z is in the forward direction, but with KiCad, Z is in the up direction. So we need to have Z up and X forward, for example. With that done, you can then select your WRL file, import it. Wait for a while because it's a fairly huge file.
Anuj, we have a quick question.
Yeah.
So basically, Amit is asking, does Blender support this in command line mode? Can we do these things?
I guess so, but it's more of a artistic visual tool. So I'm not too sure if they might be, but unfortunately, I'm the wrong guy to ask that question because for me, software stops at having learned basic 30 or 40 years back.
Right.
So
Okay. Thanks.
a good way to get an answer to that would be the Blender forum. It's pretty active, and you can kind of get all the help there. Obviously, like with any other open source tool. Also, if you're new to Blender and want to get started, what I did was follow a tutorial by a guy called Andrew Price. His online name is Blender Guru, and he's got this donut tutorials for Blender. Usually, everyone starts off with that who wants to get going with Blender, and it's a really nice introduction to getting started with the basics of Blender. And I think that really helped me understand most of the things that I needed to learn to get working with PCBs in Blender. So let me also explain a couple of other essential stuff that goes on here. Just like most of the CAD programs, Blender has a lot of different things for different people. So depending on what you are trying to do, you could be doing, let's say, modeling. So there's a separate modeling toolbar, as you call it, for example. Or if you're doing sculpting, or if you're doing UV editing, texture painting. Most of the time, in my case, I was sticking to layout and compositing, which I'll talk about a bit later. For each element you select on in Blender, you have a lot of tabs over here on the right side of the screen, which some are global and some are specific to the item that you have selected. Now, one of the things that needs to be changed is in render. The rendering process is handled by an internal engine, and there's a couple of different engines available. The two main ones are EVI and Cycles. EVI is the real-time rendering engine, which means it does things instantly or on the spot. But the result is obviously not all that awesome because it doesn't churn data sufficiently to get nice results. On the other hand, Cycles is what everyone else uses and what is recommended nowadays because EVI is pretty old. So Cycles is computational kind of an engine. So you have to ask it to render, and then it takes quite a bit of time before it spits out a final image. But the result is really much better. So you need to make sure that you have selected cycles, and there is a layers property here, and in layers you need to enable one particular item. Okay. Yeah. So there is one particular check mark that you need to enable that's called denoising data. What happens with rendering is some faces or areas of your image might have a lot of noise which appears as speckles or dots and reduces the quality of your render. So denoising data tries to overcome that, and it does a pretty good job. Apparently, and since I'm pretty new to render, the the older way of doing this was quite complicated and involved a lot of steps, but things are much easier now. So you need to check mark denoising data, and I think that's about it. The rest we can work out as we go along. Yeah. So these are the two things. Make sure your render engine is set to cycles, and in your layers you have denoising data check. With that done, in order to be able to use denoising data, you have to do an extra step, and you do that by using the compositing tool. Once you do that, if you don't see anything, use this check mark called use node. When you do that, you get this. You have rendered layers and you have the output that goes out. And those of you stuff like Rhino and stuff and other similar programs know what how this works. Like these are different nodes where you can set properties, and that's how it goes. So for the denoising to work, we need to add a denoising function between the layers and the final output. And you do that by adding the denoise function, which you use, I think, A for add. Shift A. Okay. So do a Shift A. That brings up the different kind of stuff that you can add over here. Things like adding different filters, or if you want to distort stuff and so on. If you want to change color, but what we are looking for is easiest done by looking in search. So denoise brings you this denoise function. You drop it here in the middle between the layers and the output. And what you want to now do is, instead of using the image being connected to image, you'll notice the colored dots. So usually with Blender, the similar colors connect to each other. So yellow goes to yellow, blue goes to blue, and so on. You can't connect the other colors that are grayed out at the moment. So right now, the image output is going as an image input to denoise, but we want to change and bring the noisy image as the input to the denoising image. We also want the normal, so blue goes to blue, and we need the albedo, which is here. So connecting these three and passing them through the denoise function before it goes to composite. Make sure that your output is free of noise artifacts, and it makes for a really nice, let's say, render images compared to ones without this function. So that's all you need to do. Add denoise over here and connect these three nodes to these three nodes. So once you do that, we can go back to layout, and we're now pretty much set for working on this circuit board. The other thing we can do is look at how the different view options work. So at the top over here, there are these little global icons. The last one is what looks like your final render. Then there's a lot. Then there's there's the viewport, and there's an X-ray mode, for example. So that shows you everything that's hidden. This is kind of handy when you want to select everything as a block like this. So once you do that, it selects all of these. Now, the next thing I need to do is add them to collection.
Also, Anand, we are all practically at the end of our time slot. So, if you want to start.
Okay, so here's my suggestion. I have I have this pretty much documented as a video tutorial. So maybe I can just add 4 links to it. It's there on Hackaday as a course. And,
Yes, I've added 2 links to the chat already. One is your Remoticon talk from last month, and the other is your Hackaday course.
Yeah, so the Remoticon talk is focused purely on the Blender side. So that is useful for anyone who wants to, let's say, get into the Blender side of things. Whereas the Hackaday U course is more on the KiCad and KiCad side of things.
Right.
Depending on what folks want. Yeah, like I quite often say, going through Blender, KiCad, KiCad is like drinking water from a fire hose. It's like there's just too much stuff flowing and too little time. So it's never easy to compress it into. But I'm happy to answer questions because that might be more important than actually going through the whole steps, which might be more tedious.
Yeah, so I think Amit had a couple of questions. So one was the command line mode. There were a couple of appreciative things about some of the things that you talked about. There's one other thing that Amit was talking about, which I don't think he's very sure, but is you'll basically have to create our own library of parts connectors before you can use them inside Blender. Right?
No, not really, because the input to Blender is the exported output from KiCad. So in KiCad, let me just show you very quickly. I'll just share screen, right? So in KiCad, when you make a circuit board, it fires up everything. The file export VRML. So that produces a VRML file that would be the input to Blender.
Okay. And typically FreeCAD will take something like a step, right? That should be good.
Yeah, so if you're working with FreeCAD, you prefer to have step files. In Blender, this VRML is what works. Okay. The other thing, the other quirk with Blender is units. So Blender has what's known as Blender units, which is like unitless. One is one. So apparently what happens is when you export from KiCad, 1 millimeter in KiCad ends up like being 1 inch in Blender or some such vague thing. So you have these circuit boards that are like massively huge. And it's okay in the sense that you can still work with it, but if you are trying to do real world modeling, then you have to scale things down to do that. And because the VRML file is not a native Blender object, you can't scale it by just choosing preferences. You have to actually select the object and say, okay, now scale it down to this dimension. So there's an extra step involved in it. Like if it was a standard Blender object, you can make it exactly 1 mm or 1 inch or 1 kilometer.
Right. So do you think KiCad folks are working on making this easier going forward?
I don't think it's a KiCad issue really. And apparently, it's also something that you can't say it as a Blender issue. You just have to live with it. Maybe there is some way to program it. Maybe there's a way to programmatically do it. For example, if you can edit the WRL file and
Maybe the KiCad extension.
yeah, and just scale it so that when Blender opens it, it's already at the right scale.
Right.
But I don't think there is an easy way to it. Also, I noticed rendering is extremely time consuming, and I mean, you need a ton of patience. Like, you can't just feel your way through it. There are a lot of things that have to be done manually, whether you like it or not.
Right. I think that's what Amit was kind of getting to. Like, he was
Yeah.
wondering how he can basically get to a point where he can automatically do it, because I think that's the PCB kingdom way of doing things.
Right.
But yeah, so I think that's what he was wondering. But it seems like
But you know what?
there's still
You
some
can
stuff.
get really nice results by just doing the KiCad plus FreeCAD route without involving Blender. You can get pretty close.
Right.
And there is a ray tracing workbench in KiCad in FreeCAD. Sorry. So and some work is being done on it. It's not perfect yet, and I have not been able to figure out how it works yet. But if that works, then you probably don't need Blender at all. You can do everything within KiCad plus FreeCAD,
Right.
which will be ideal.
Cool. Yeah.
So sorry for overstepping. I think we're 10 minutes over the counter. But
Yeah. Jitin is already here. Hey, Jitin.
I
So
met
sorry.
Jitin long back when he showed me the X-Pies demo in Delhi. It was many years
The
back at
Delhi
Maker.
conference, probably.
No, at Maker's Asylum.
Ah, yes. Okay. It's about 4 years back. Yes.
More than 4 years, actually. So
Yeah, I think.
anyway, happy to have you here and excited to look forward to our talk. So I'm over and out, Anuj.
Yeah, thanks, Anul. Anul will be there in the comments as well as Telegram. So if anyone wants to, I've also linked his Twitter handle on the conf page. So please feel free to get in touch with him if you have any questions about his talk. Thanks, Anul.
Okay, happy to help.
All right, Jitin, first of all, sorry for keeping you waiting for
not
10
an issue.
minutes. Yeah, but we got like the first talk added 5 minutes, the second talk added 5 minutes more. So
I will subtract 5.
no worries. But yeah, you don't really have any restrictions because yours is the last talk for today, and then tomorrow we have I think 4 more talks starting from 4 p.m.
Okay.
So without further ado, I won't keep everyone waiting. And Jitin, it's all on you. So just hit the share screen at the bottom.
Yeah, and can you like stay around here just as a mod?
Yeah, I will obviously be there. I'll shut off my video and be away, but I'll still be there.
Yeah, okay. This is good, right?
Yeah, this is good. We can see.
Okay. So hey everyone, my name is Jitin, and I work at CSpark Research. And what we do is we develop data acquisition instruments, a variety of instruments that get data from the physical world, from any sort of parameters, and onto a computer for the purpose of science experiments. And the audience that we target goes from school level, where kids may be interested in knowing, let's say, how bright is a certain light or an LED, or how humid is the room. Very simple parameters. And all the way up to research labs, where we developed radiation detectors for alpha, gamma, beta radiations. And let me just go to my slideshow here. Okay, so in this talk, I'll be basically outlining the various steps that I follow when we're developing all these instruments. So for the first part, you have a microcontroller interfaced with a sensor, which is the hardware part. For example, here I have a simple dev board, just a microcontroller with USB connectivity to my laptop, and I have to handle the communication part. And in order to get that data and display it on the laptop, there'll be some software running on your PC, desktop, laptop, whatever, which can visualize this data, analyze this data, and so forth. And to demonstrate, I'll be taking two instruments which I've been working on closely. One is QtPy, which is a very elementary project which designed to teach microcontrollers how to program microcontrollers. Taking one look at the photo, you're probably thinking this is some sort of dev board, which it is, but the difference it has from, let's say, an Arduino is that the bootloader is slightly more functional, wherein you can use a connected PC to tweak each register in real time without compiling and uploading code. And there are also some layers which allow you to connect sensors to this and directly get data onto a PC without actually compiling, uploading code of your own. And I'm also going to talk about XSpice, which is a more complicated instrument, again, centered around a microcontroller with some analog instruments around it, peripherals. And it can do a host of things like measure voltages, it's an oscilloscope, measure resistances, capacitances, and so on and so forth. And yeah, so this is how I would break down the instrument. On the bottom half, you have the hardware, which, for example, Anuj, can you see this clearly? I'm not sure if it's clear enough.
Yeah, I think it's good enough.
I mean, you can figure out that there's a hardware instrument, right? And inside this hardware instrument, you have a processor with some analog circuitry, and it can interface with a host of measurement devices, some of which are built in for voltages, time signals, etc., and some of which are commercially available. For example, I have here a pressure sensor, a few ₹100. I have an accelerometer, an angular velocity sensor, again, a few ₹100, humidity sensor, light intensity, so on and so forth. And what it does is it has all the protocols for communicating with these sensors already written into it. So students can go on and use abstraction layers, like simple functions for, let's say, read humidity. And it'll return the value in RH units of whatever the humidity parameter is by getting data from the sensor through the instrument and to your laptop, where you can visualize it. So as shown in the previous slide, you could connect something here to this instrument and see gauges where this is pressure, this is temperature, and okay, some parameters not working for, let's say, physics experiments, electronics experiments, so forth. Yeah, so there are two parts to the software. One is the firmware, which is code that will run on the microcontroller. So, for example, here I have a small snippet which reads the register and dumps it to the serial port. So there's a command set. If I receive a certain byte, the microcontroller knows, okay, I need to do this, and then it'll return a certain value. And on the Python side of things, which is the library on the PC, you have code to read that register, and then you can do whatever you want with it. So there's two parts to the code that we write. And the same implementation, for example, a complex function called measure frequency, for which runs on XSpice. It can measure frequency up to 8 megahertz. And this is the C part of things, and this is the Python part of things. In the middle, you have a communication interface, which is USB and a serial converter. Okay, so the outline of all the tools that we use. First is the hardware design. So we do the hardware design in KiCad, and as Anul showed, you can take the hardware design, export it into a step file or a WRML file, and render it in Blender. But the thing is, we need to design enclosures for these instruments, which need to be in real units. And I'm not very comfortable with Blender. So what I use is something called SolidWorks, which is proprietary, but that's the approach I follow. So I'll just quickly show you. This is the layout for QtPy. So you can see the board here. It's not the same as what I just showed you because this uses a different package for the Atmega processor. The one that I have here is a DIP package. It's big. And KiCad will give me a 3D render for this. And I can export this, not from here. I can export this file into a WRML file, which I then import into SolidWorks, and I can use that. Yeah. So my board exported with KiCad, centered around this, I can develop an enclosure and see if everything fits. And these files for the enclosure then go to the injection molding designer, who will then generate a plastic enclosure for it. Okay, sorry. Coming back. Right. Okay, so once you have the hardware, you need to handle communications where, okay, a Python module called PySerial is used. If I'm using a laptop, if I'm using Android, there'll be libraries corresponding to that. Then you need a graphical interface. So since most of our software is written in Python, we use the PyQt widget library, and PyQt Graph is a very good plotting library. It's pretty fantastic, fast, and works very well with large data sets. Then we use NumPy and SciPy for analysis. For example, when you get raw data representing a sine wave, you want to extract the frequency associated with it, you will need some library that's very good at math. Then there's an important part, documentation. People can't really use the interface or the hardware if there's not proper documentation. So what we do is we have all the documentation in plain text markdown formats, which is then compiled into PDF forms or visually attractive HTML formats, etc. And I'll give you a short demo. I'm just going to run through all this and then I'll jump to a demo. Then there's packaging. For Python programs, on Ubuntu, we generate deb files, which are one-click installers for the software. And on Windows, we use PyInstaller, which is a module which sort of bundles the Python interpreter, all the modules used in a particular software into one directory from where it's standalone. So you can copy paste that directory and run it. And that can further be converted into an installer by using a tool. It's a free tool called InnoSetup. And then there's Inkscape, which is great with vector graphics, and that's what we use for generating, all the properly aligned labels which go on the plastic boxes. So this is Kutibai's layout and the 3D render for the same. And this is the pinout diagram. There's very few parts on this board, just the processor with a different bootloader. There's an RGB LED to quickly see if things are working or not. And there's the software. So the software, if you observe, it just mirrors the hardware itself. There's a lot of pins here which represent the pins here. And it's like a real-time monitoring tool for the Kutipai. Let me just jump to the code and run it and show you how it works. So I have here, sorry. I have loose connection here. Sorry. Or I think it was already running, or 1 second. Yeah. So I have a loose cable. I'm sorry. 1 second. Yeah. So you have 32 I/O pins here. They're grouped into ports. And okay, so I have my USB port is thoroughly abused. Yeah, and what you see here is the live status of every input pin here. So I have 32 pins, and all of these are shown either as low, which is red, or as high, which is green. Now, if I touch this, you can see them fluctuating in real time. Okay, so it's stray charges from my fingers actually causing, so it's real data coming here on the fly. Now, if I want to convert an input to an output, for example, this PD7, it's in a blue outline because that PD7 has a track connected to the blue part of this RGB LED here. So I can convert it to an output type, and I can turn it on, and you can see that in real time, it's, you can toggle it. And the important part here is it's designed to teach microcontrollers. So every change that you make is shown here saying, port D is set to 0. That's how PD7 is off. If I turn on PD7, the command that was written as port D is now 128. In binaries, that's 1 followed by 7 zeros. Similarly, if I want PD0 or let's say PD5 also high, I just turn it to output. So to make both of these output, DDRD is set to a value of 160. Turn on both of them. So that's a cyan color. That's a mix of blue and green. And you have port D set to 160. So that's some of the features of the microcontroller that's directly interfaced with your laptop. Now there are other I didn't want to add any analog things to it. It has to be as simple as possible, just for just to take out the step of compiling and uploading, and directly tweak registers and see what happens. At the same time, it has utility as a software real world bridge. If you want to write a Python script to control, let's say, the lights in your room, you could take this, connect a relay, and you use that relay to write some Python code to turn on and off code, lights and so on. And there'll be other complex functions available. For example, this one also has a PWM output. So when I set it to PWM mode, there are 3 registers that need to be written to certain values that were written there. And here I'm tweaking the blue intensity. Let me turn off the green one. So yeah, that's PWM value is being toggled, so I can fade the blue LED to certain values. Okay, now, as I was mentioning before, there are sensors available for pretty much every physical parameter you can measure, from temperature, humidity, light intensity, magnetic field, so on and so forth. And they're really cheap sensors, but and they find tremendous application in physics labs. For example, if you want to teach high schoolers what the magnetic field inside a solenoid is, they teach it in theory. If you have a large solenoid, the field along the axis is constant, and on the edges it falls off like that. So they never get to measure, they never actually get to visualize it, measure it, because the instrument, it's not available in most schools because it's expensive, it's a big box, and you need to plot, so on and so forth. But you don't need all that. You have very cheap magnetometers because they're used in your phones as compasses. So the IC itself is commercially made by millions of units, so it's cheap. And I'm just going to pick up one of these. Where is my? Sorry, it's on the floor. Yeah. So I have. So I'm using these cables, aux cables with 4 wires in them, and here I have connected a pressure sensor, and it also measures temperature. So I'm just going to plug it into this board. And the communication protocol that's used here is I2C. It uses 4 wires, a supply, ground, a clock signal, and a data signal. Data signal is 2-way. And here I can simply scan for the sensor connected. And it says this sensor is connected, BMP280, at this particular address. So these sensors can be parallelized. You can have multiple sensors as long as they have different addresses. And here. So what you see on the screen is live readings of pressure, of temperature in my room, and this is humidity, which is available if I connect a BME280 instead of the BMP280 sensor, which I have here. And how do I change the pressure? So I can change the pressure that way, and temperature, you can see it go up and down. And one rather simple experiment which I like to show with this is variation of pressure with altitude. So they teach you in schools that as you go up into the hills, pressure drops. Okay, and yes, if you go into the hills, you can actually feel it in your ears and so on. But you can actually measure it with this. How? Let me just... so this is the pressure here, 986.7. That's pressure in Delhi. If I just raise it, you can see the pressure drop. And if I lower the sensor, so that's the sort of resolution that sensors, which this one cost, I think, 100 rupees or something, that's there, but it's not being used in schools because, again, cost barriers. And so that's one sensor that you can use to demonstrate simple principles that are taught in theory. And another one, let's say I can have, okay, I'll come to more ones. Let me just move on with my slide. I'm already out 20 minutes. Yeah. So what we have here, we have a software that looks like the hardware, so that you can easily figure out what it does. And at the same time, it does not compromise on the part where you can actually compile and upload C files to it. So let me. So if I want to upload some code, I can go open some C file. Let's say I have a persistence of vision code example here. This code example blinks LEDs in a certain fashion to write in air. It's called persistence of vision. And I can compile and upload that code. Oops, 1 second. One second. Okay. Yeah. So it's compiled and uploaded. But the thing is, microcontrollers don't have a scheduler to run multiple programs at the same time. It's either one or the other. So when I said the bootloader handles this entire part of toggling registers in real time with the laptop, it means that the bootloader is running. Right now, the code that you've uploaded, it's there, but execution has not been passed to it, which you can instruct the bootloader to do so. I say user app. So now the user app is running, which is a persistence of vision display. I don't know if you can see it through webcam, but if I move this like that, you can actually see it writing in air, or it gets disconnected. So if it's disconnected, then it's running the default program that's loaded here. Okay, so that's not sure you can see it, but Anuj, can you see any text being written in air, or is my camera's frame rate too fast?
I can see Kutti.
Okay, so you can read it. So you get the idea,
Yeah,
right?
yeah.
So it's 8 LEDs blinking in successive fashion to actually write in air. It's a pretty simple concept, fascinating. And I try to improve upon the IDE a little bit by introducing features that allow you to log data sent by the microcontroller, your code running on the microcontroller. So for example, if I have here, I have a small program that just dumps integers. Yeah, it just generates integers and puts them into the console, serial port. And just if I compile and upload that program, run it. Yeah. Okay, so what this is doing is it's taking numbers from 1 to 10,000 and just dumping it on the serial port. And here we have some handy features to actually read that data, plot it as a gauge, or plot it in the data logger as a graph. So you can make maybe some more instruments of your own and debug them quickly, see that things are working and so on. Okay, so let's move on to other things that. Okay,
this is a quick question, if
yeah.
you don't mind. So Milind is asking, is the board using REPL in the backend?
What is REPL?
REPL is the Python thing that basically lets you interact with it, like
Where can
read,
I
eval,
see?
print.
No, where can I see the comments? Okay, yeah.
It's on the screen right
Is the
now.
board using REP? No. So it's okay. So it's pretty basic in what it does. There is the bootloader which you have for the Arduino Uno for the Atmega series. Okay, and it's called OptiBoot. So what I've done is I've taken a fork of OptiBoot and I've added like a few set of additional commands. So bootloader accepts commands, right? Okay, 1 byte represents that, okay, the subsequent bytes need to be stored into flash. Another maybe, let's say, return the version number of the bootloader or the chip ID and things like that. So I added a couple of more things to it, which allow you to tweak registers in real time. Through the bootloader, not actually compiling, uploading code, nothing of that sort. So there's no REPL. There is just a set of bytes. There are bytes. If you look at the code, let me just show you the code here. I need to turn on my screen share 1 second. Is my screen share on? Yeah.
Yeah, it's on.
So if you look at the code, let me just look at get version maybe. Yeah, so get version is just byte.pack1. It's the number 1, and the okay. So the get version function does 2 things. One is it resets the chip to make it go into bootloader mode. So the moment you call get version, if your code is running on it on the hardware, it'll stop execution, go back to the bootloader mode because the reset has been invoked. Now the bootloader will get command of it. You will send the get version thing, and then you'll just read back a number, which is the version. And you see if it matches with the version that's meant for Atmega 32. I just have like 3-4 command sets and some specific ones for I2C communication so that things are faster for reading from sensors. And nothing more. The bootloader is still like 500 kilobytes something. 500 bytes something. It's pretty small. Now, okay, have I had difficulties, resistance, friction introducing this to students? Actually, no, it went pretty well. But the thing is, it's I can't spend much time on it because one, it doesn't make money unless sold in very large numbers. And if I can run a marketing campaign for this, I think it has more potential than Arduino in the sense that it does more, in terms of a data. Because a lot of people make projects where they write their own communication protocols to get data from an Arduino Uno to laptop, then write their own visualization code and so on and so forth. All that is cut out for them. It has a market in physics students educators and so forth. For the price of, I have these boards in stock. I sell them for like 650. That's just the cost of the board and the cable and just one of these LED boards. And then you can just plug and play whatever sensors you have. If I have an accelerometer or an angular velocity sensor, yeah, for example, if I have this here, I have an accelerometer and an angular velocity sensor plugged in, and I just scan for it. It's here. So you see, these are values from the accelerometer. The first three, the last three are from the angular velocity sensor. And so if I just make this oscillate, accelerometer values won't change much because it's just tilting slightly. Okay, so the tilt can be measured with the first three because it's a component of 9.8, the value of gravity. And the last three are measuring angular velocity. So if it's rotating, the last three can be looked at. So I can take this and go to the data logger, and I can even do a sine fit, which will give me the oscillating frequencies. That's 1.55 hertz. I can use this to develop experiments. Let's say a simple pendulum. I attach a sensor to a simple pendulum, let it oscillate, calculate frequency, calculate damping coefficients, so on and so forth. Right, I need to skip forward. Okay, I need to skip forward to the, there's a lot more slides, I think. Yeah, a lot more slides. I hope that answers your question. Okay, so since the Arduino Uno uses, again, the Atmega 32 series, 328, I think, you can just compile the firmware, which is there in the Git repo. I have linked it in the last slide. You'll find links, but it's yeah, here, Kutipai GUI. Inside here, you'll find in the docs, you'll find the firmware, and you just need to compile it with the appropriate processor that you're using. I'm compiling it for Atmega 32, and okay, there's also an Android app for connecting the Gotibai to your phone. It's a pretty basic thing, but it has all the features. You can actually read all the pin status, controls, output, input, and also check out the values from connected sensors, view them as gauges and such. Yeah, so this is another UI that's part of the package for the Arduino Uno, which again, if you can flash the firmware onto your Uno's it will still function as an Arduino Uno. I haven't checked it with the Arduino IDE, but it works with the Kutipai IDE. You can compile and upload code for this thing. And the layout is slightly changed to represent the pins that are here on the Uno. And there's one for Nano as well. Okay, so now I'll come to XSpice, which is sorry, I just disconnected the Kutipai. So okay, so which is a fairly more complex instrument. It has a lot of analog input channels, and it's calibrated to give accurate readings, 1 millivolt resolution, 1 millivolt accuracy, and it has a lot of things. Let me just quickly go on to this thing. So once you have the hardware that is capable of executing certain tasks and sending data over to your laptop, you need to be able to visualize that data, analyze, and so on and so forth. So you need a graphical interface. So what I've used is PyQt, and first you use the Qt Designer, where you can set up where all the buttons need to be. You can link buttons to functions and so on, and then you write Python code which will actually implement those functions. There are several tutorials on how to do this. You don't need to get into that. I'll show you some sample experiments. Some things you can do. For example, here I have a DC motor connected to a pendulum. So motors, when you apply voltage, DC motors, you have a coil and a magnet, and you have, the motor will rotate. But the opposite is also true. If you rotate the motor, there's a coil moving in a magnetic field. So a voltage is induced. That induced voltage is proportional to the velocity. So if you just want to find out the time period of a pendulum, you can attach it to a motor as a shaft, and you measure the induced voltage as a function of time. And you can, from that, you can measure the damping coefficient and the frequency of oscillations. And then you can, this is a very simple, I think, class 11th or class 10th experiment where you calculate the value of G, acceleration due to gravity. You can do the same thing with an accelerometer sensor, where I have connected the sensor to a shaft here. The values from the sensor are being plotted here. So the accelerometer gives you the angle of inclination, which will be your theta, and the angular velocity again is measured directly with the angular velocity sensor, not by taking a derivative, and that's your omega. And you can see here wherever theta is zero, wherever theta is at the extremes, you have the velocity is zero, which because the pendulum stops at extremes, and whenever theta is at the mean position, you have the velocity maximum in either direction. So you have a 90-degree phase shift, which you can observe here. Let me show you a LiDAR. I have, yeah, it's already plugged in. So I have a small sensor which measures distance using light. Again, it's not very expensive. Let me just go to the UI. Okay, let's disconnect this. So this is the UI for XSpice. There are 4 oscilloscope channels. There are waveform generators. There are voltage outputs. There's capacitance measurement, frequency, so on and so forth. So I have a waveform generator WG. Let me tilt my camera to wait 1 second. Yeah, I think this is roughly good enough. Yeah, this should work. Okay, so what I'm going to do is I'm going to take the waveform generator output here and plug it into an oscilloscope input here. So you can see the sine waves there, and I can also change the frequency of the waveform generator, and the oscilloscope will read it. Now, okay, they're both in the same device, both instruments. So let me take an external source. Let me take the microphone input. Forget about this one. So the mic input is now recording me. Okay, so I'm just going to whistle. So you can hear the sound of my whistling, right? Now, if I wanted to know the frequency of this, since this data is collected as a function of time very accurately, I can use NumPy or I can use SciPy's least square fitting module to extract the frequency. Watch this space. So it's about 2100 hertz. 2500 hertz. Now, this is only if it's a pure sine wave, because we're approximating this to a pure sine wave. If I have a mix of 2 signals, how do I generate a mix of 2 signals? I'm going to take a piezo buzzer and I'm going to connect it to WG. And this buzzer has a resonance, maximum resonance at around 3500 hertz, which means it's loudest in that region and the amplitude is lesser at other regions. So I'm not sure you can hear this, but around 3500. Okay, 3000 for this one. You can see that you can actually see that the amplitude it's loud. Okay, and the frequency is 3035 hertz, which is what we set. Now, if I take a Fourier transform of this, so this is an excellent way to demonstrate to students what a Fourier transform actually does. Okay, it converts, I mean, I was thoroughly confused when I was in 11th, 12th, so on, where we were taught that, okay, there's something called a Fourier transform. It's a bunch of formulas, but if you can visualize it, it makes a lot more sense. So there is one peak for a pure sine wave. Now let me create a mix. So what you can see here is you have a secondary wave here. This was my whistling, and this is the main buzzer. Let me make my whistling a little louder. There. So I have a louder peak, so on. So this frequency is what I was whistling at, and this is what the fundamental frequency of the buzzer was. Okay, so now let me show you. 1 second. Looking for a buzzer. Okay, so just right. So I was just going to show you the LiDAR I'm just going to go back to that. Go to I2C modules, I2C sensors, scan. There's a LiDAR connected. Let me just drill down to that again. Yeah. So this is the LiDAR, and the light is going to emit from this, bounce off my hand, go back to this. It'll calculate the round trip time, and from the speed of light, it'll show you what the distance is. There. So you see, this can be used to measure distance using light. And again, if this was a simple mass spring system and you wanted to know what the frequency was, you could do something like 1 second. A sine fit of this data, and the frequency is 1.65 hertz, which makes sense. Okay. Okay, there's a host of plug-and-play sensors that you can get off the market and use. Okay, now let me do a little fancy experiment, and this will sort of explain to you why it makes a lot more sense to get data onto a computer. I have something called the advanced data logger. So what it does is you can set any X parameter, any value. For example, you want voltage going from, let's say, -2 volts to 3 volts in steps of 0.1 volts. And for each data point on the X-axis, you measure one data point on the Y-axis, which could, again, be any other parameter. So what I want to do is I want to check where this piezo buzzer is loudest. Like I said, it's loudest at around 3000 hertz, but I want to be sure, like, where is it exactly? So I'll choose the X parameter, which will be the waveform generator, where I've connected my buzzer. Let me just check it. So yeah, I can hear it, which means it's working. And I needed to go from, let's say, 1000 hertz. Below that, you won't be able to hear anything anyway, to 5000 hertz, confirm. And the Y parameter, that's a little tricky. That needs to be the amplitude of this. So for that, you need to measure, you take the oscilloscope, pick the microphone channel. Okay. From that, you need the amplitude. Cross-check frequency, just to check that it's not some other frequency, to avoid wrong fittings and noise and so on. And the amplitude maximum you'll get is 3 volts for this thing. So I'll just set it to 3 volts, 0 to 3 volts, confirm. Time interval 50 milliseconds. Settling time around 100 milliseconds, because every time you set a new frequency, the buzzer takes some time to respond. Now, just log data. Did you get that? 1 second. Anuj, are you still there? Can you just like give me some feedback?
Yeah, I'm still here.
Yeah. So what we did here was that we took. Let me take more points just to. So what this is doing is it's setting a frequency on the output waveform generator, which the buzzer then emits, which is then collected by the mic, analyzed, amplitude is extracted.
So it's essentially a signal generator as well as data acquisition.
Yes. So what we can observe here is that this has two resonances. It's loudest at 3000 something, and it's also equally loudest at 4000 some hertz. Okay, now instead of using a sine wave, if I use a square wave, what is the expected behavior? Right, my X parameter is going to be square, SQ2, the square wave generator. Again, all the way to 5000 hertz only, from let's say 100 hertz this time. Let me just take the data and then we'll explain it. Okay, so I had some ambient noise, and but you can see roughly that, okay, at square at 3000 you had a peak as before with the sine wave, at 4000 as well. But what do you see here? At 3000 divided by 3 you have similar pattern, right? The 4000 here is here, 3000 by 3 is here. Again, you have something at 3000 by 5. This is roughly. So why is this? This is something which we study in school, which is the components of a square wave. A square wave is actually composed of sine waves, right? You have the fundamental, you have 3 times the frequency, 5 times, 7 times, so on. That's how you create a square from sine waves. So what the piezo buzzer does is, it can only resonate at 3000. So if you give it only 1000 hertz, it'll pick the next harmonic, that's 3000, and resonate with that. So it'll go to the closest frequency and try to catch onto that, whatever's available. And this is a clean data set which I got with a different piezo, not this one. And you can see at 1/5, at 1/3, at 1/5, 1/7, you can see peaks all the way down to 10 hertz. And similarly, instead of looking at amplitude, if I look at frequency, you can see that frequency is never between the recorded frequency, not the applied one. It's never between any of these available ones. So it's always latching onto either 3x, 5x, 7x, 9x, so on. Yeah, okay, so this is this brings me to the end of my talk. Packaging, what I've used spines.
Jitin,
Yeah.
is the
Yes.
piezo still on?
Oh, the piezo is still on. Yes, sorry.
Yeah.
I can barely hear it. I have these. Sorry. Yeah, this brings me to the pretty much the end of my talk. How I've packaged this for Ubuntu Debian systems. It's simple. We have we have a maintainer for the official repo, Debian repository, and for the latest debs, we also package our own deb files and send it across. For Windows, you have PyInstaller, which makes a bundle of the software, and which then we use InnoSetup to package it into one-click installers. Then there's also PyPy, where you can push the latest code that's there. Internationalization. Oh yeah, this is for XPies. It also goes into a lot of rural locations where you need local languages. And for that, since all our documentation, which I did not show, if you just pick any, let's say an experiment, plot IV, XY plotting, whatever. So there is a enable pop-up help window option here, where if you select it, sorry, just clicked it twice. It'll show a pop-up window where there'll be some plots, some instructions, theory on how to do the experiments. And this is all in plain text, the actual content. And this can be translated into different languages. And once you, when you install the software, you can select which language you want, and then it's built into PDF, the HTML formats for the software, and so on. So this is the English user manual, which you have a lot of sections. It all comes from these small MD files. It's compiled with a large script, which George wrote. He's one of the maintainers. He's the maintainer. He also translated it into French, where he uses it in France. And there is a Malayalam interface contributed by Amal. I can just go here and switch to choose language. I want Malayalam. So you see my UI is now in Malayalam.
Wow.
Everything is in Malayalam. And
Nice.
I can, yeah, so this is all text that's been translated into Malayalam for high schoolers. So on. Let's go back to small icon for language. English. And there's some work on a remote access server where you can write, we use Flask as a backend server, and you can remotely acquire data. Not a priority at the time. Yeah, so this is some of the things we do with QtPy. You can connect a PWM generator sensor, which I then connect to a bunch of servo motors connected to this Mi arm, robotic arm. And then using the UI, you can control this robotic arm through Python code, simple code. These are links to all the design files. Both these are open hardware. You can find all the layouts, schematics, everything. I'll just show the tabs also. So yeah, QtPy GUI is here, which has support for Uno and Nano. Other boards can be added if somebody is up to it. There's a document, read the docs page for QtPy, where you can have all sorts of the experiments that you can do with it, the sensors, how to, there are Python calls for everything. So that's all documented here. they're all one-line codes. For example, TSL2561 initialize a light sensor and then just read values from that light sensor and then print it. So it's like 2-3 lines for everything. Just like 4 lines of code, you should be able to get data from a light sensor and then use it. It's designed for very beginners to coding, people who are interested more in the data for the sensors rather than the code itself or the engineering part. This is the page for XSpice. Everything for XSpice goes here. Where do you buy it? Where do you all the software, everything. Then you have the repo for XSpice, again linked in the slides. The Android thing, the docs. This is everything that we have for at CSpark Research. All the instruments that we do work on. Yeah, so that brings me to the end of my talk. I think I'm over 5 minutes also.
We have a couple of questions. So
Yes.
with the ones that came first. So Milind was asking, so essentially the bootloader is acting like a DMA for the port registers and the I2C, right?
Wait, it's... yeah, I mean, a DMA is a separate module independent from the CPU that lets you, take data. That's I use the DMA frequently in XSpice, but well, it's yeah, you could compare it to a DMA. It's the job of the bootloader is just functionality, something like that. You take it's not direct. There is a middle. It'll interpret your command and then read that register. It can also interpret different commands. So it's not a complete free pass through like a DMA, but it's something along those lines.
Yeah.
So
there's another question from Milind. So how the phone communicates with the port?
So your phone has this USB port where you can attach a USB OTG cable, which you may have used for connecting pen drives, but at the same time you can connect this also to your phone.
So this probably limits it only to Android.
Yes, Android, yes, because iOS charges you a ton for hardware capabilities. I need a license for that. So yeah, that's not my target audience anyway. So
yeah,
Android phones, even the low-end phones, it'll work fine.
Yeah. I had a question. So does it work with the Raspberry Pi? So let's
it does. Yeah. All this works with Raspberry Pi. It works with which processor? ARM7? You mean?
ARM7 is the Raspberry Pi 3, basically. And
It's been thoroughly tested on Raspberry Pi. Even XSpice works on Raspberry Pi. It takes less than 200 milliamperes, so that's pretty much. And on Raspberry Pi, we had this small issue of packets dropping, but it'll still work. At high speed, so we had to bump down the speed a little.
Bump down the speed on what end?
On the whole communications speed.
Okay.
So it worked better on Orange Pi instead of Raspberry Pi. So we made some devices which Orange Pi combined with the Raspberry. Orange Pi is another. It's about less than half the price, but it's sort of faster. I felt it was faster. You could. Yeah. So it worked fine there, but it still works fine. Packet drops are handled smoothly. So.
Packet drops were on Raspberry Pi 3?
Raspberry Pi 3, I think. 4 I have not tested so far. I don't have it. Right. And QtPi will work fine. It works on a smaller, lesser communication speed already, so not an issue.
Nice.
It should work on. Yes, Desh has inputs. Basically, anything that boots a Linux distro. Yes.
Yes. Milind is like.
And Windows.
Oh, of course. There might be very few Windows users. We had Anul earlier, but I think there's very few Windows users on the chat. Melinda asks another question: is why name it QtPi?
Kuti is a child in Malayalam, so that's how QtPi came out be. So QtPi, the concept was my dad's, so he named it QtPi at the time. So at the time, what he had was this board with a Python library with which two functions, set register, get register. And there was a firmware, like a normal firmware. The bootloader was not involved. There is a firmware whose job is to read and write registers. So now you can use Python command lines to, just toggle registers. And then I started playing with this and I figured, why not make a UI for it? Then I had a real-time UI where you can visualize the entire input sets, output sets, toggle, play around. Then it also meant that, either the QtPi firmware will run or your code will run. which means you had to wipe one to get the other. Then I started playing around with the bootloader, and I figured, if the bootloader can do this, then you don't need to touch the user space for the code will still be there available, and
Right.
it'll be sort of enhanced bootloader with more
I
capabilities.
mean, enhanced is probably underselling it. I think it's a pretty. I mean, it's an application in the bootloader itself, I guess. If you look at it, because it's doing quite some stuff, right?
At the base level, it's only bumping values from here to there. Everything else, all the sensors, visualization protocols, everything is on Python side. On the hardware side, there's only like 2-3 function calls. Python will handle every specific I2C protocol for each sensor. All that is in Python. You don't need to touch the hardware to change that.
Got it. So it's okay. So it's heavy on the CPU, like
on the laptop side, because that's where
Python,
development is easier.
Yeah.
So I wouldn't hard code anything onto a small processor. So
makes sense.
Yeah.
Nice. Yeah, I think rest of the comments are pretty appreciative of the work that you're doing. I mean, honestly, if I had something like this in school and Anul agrees with me, I don't think I would have gone into engineering at all. I think I would have probably gone into physics because, I mean, for whatever reason, we had very boring physics demos that we mostly read about instead of actually trying. So this is actually pretty
yeah. So most of them, I mean, with XYZ, you can do a whole range of experiments. There's a whole list, documentation completed. There's a book on it, so you can pretty much cover electronics 101 and physics. A lot of things you basically augment whatever you're already doing in a physics lab with extra sensors. Yeah.
Nice. Plus, you get to learn some bits of programming as well, optionally. But
optional. I mean, that's you minimize. I mean, you can write your own programming,
right?
Which I mean, if you're becoming a scientist of sorts, you need to write some code. And this also introduces, sort of exposes you to the research environment where you have multiple instruments. You need to hook them up to the same script, and then have a control loop running. So this sort of approach is not followed in the current curriculum. You have black boxes which will display readings from one instrument. That will be a separate unit displaying readings from. Then you take a log, and okay, that is important in the beginning. But if you want to make fancier experiments, you need to hook up multiple things together.
I mean, it's like Lego blocks, right? Like when you give someone Lego blocks, yeah, sure, you can do what's done there on the manual that you got with it, but then you can make something else.
Yeah, you can mix and match and make your own things, and
yeah. There's some feature requests. Anul is asking for a version based on the new fancy RPi Pico.
Yeah, I don't have that board yet. I'll try to get my hands. I don't have time for R&D, but so the RPi Pico, I don't know how it's. I mean, what is the architecture? I know nothing about it. But if you can tweak the bootloader, then yes, you can have QtPy support for it. It's just about whether or not you can tweak the bootloader.
Right. I mean, I think it's as open as it can be.
So if you can,
yeah.
If somebody just enhance the bootloader set to include the QtPy commands, 3 of them. If this byte comes, you need to take the following byte and write it to a register or something like that. Then that's all. Everything else is on your PC side. It doesn't need to know anything about what's the hardware.
Yeah, I mean, and interestingly, you could also. This is probably hard to do on a Wi-Fi microcontroller like the ESP32, right? Because
you could do this on an ESP also. So ESP has this over-the-air bootloader, and so you can have a a wireless control device. Yeah, you could. I just have not spent time on it, but yeah, pretty much.
Yeah, nice. Let me just check. Yeah, I think people were pretty happy with the demos because I'm pretty sure this took everyone back to their physics labs and how they could have.
I gave very simple acoustics demos. There's plenty more we could have done, but it's so you can see there's a lot of experiments for school levels, for advanced levels, and so on and so forth. There's a whole. There are blog posts at CSpark Research.
Right. I posted the link to the GitHub page for CSpark Research. I'll also post a link.
If you can put the link to this blog, it's by some this. Here I have I've put up my resources and what you can all this data logger, everything I talked about, it's there in blog posts.
Right. Okay.
And
I posted the link to CSpark Research. I'll add that as well.
So all the steps that we follow in manufacturing, for example, if you look at my screen here,
Yeah.
all the parts that go into a pick and place machine and the stencil assembly, how it's populated, reflow ovens and so on. Then
Nice.
some experiments using sound to measure distance. I showed you using light to measure distance because it's a sensor which is pretty great. Again, there's one that uses sound. This is cheaper, about 50 rupees. You can get it in any electronics shop.
Right.
And it's fairly commonly used by people who make robots, toy robots. But it has applications in physics where you want to measure, for example, this mass spring system and plot the oscillations.
Nice.
Yeah.
There's like this is like learning to paint because there's so much you can do.
Yes. I mean, for I've tried to keep costs as low as possible by integrating everything into a small unit. And
Right. If someone wants to get one of these, how do they do that?
Yeah, so there are some online vendors, and universities typically buy directly because they have more quantity. But there are online vendors which is listed on XPice, online as well as
Okay.
offline for different states. You have multiple vendors. How to buy this section here? Yeah. So you can order online. It's about 4,000 on Fab to Lab, I think. And
Okay.
for different states, there are. So typically, if you go to buy, if you want to set up an electronics workbench, it's a huge expense. Here we've tried to. It's a certain set of tools, essentials to cover the as much as you can. So you can check out the blog if you're interested, and that's pretty much winds up my talk.
Awesome. I'll just check once more if you have any questions. But I think that's it. People are pretty happy. So again, thanks, Chetan. Like for making time. This was a pretty awesome
Thank
demo.
you for having me here.
And yeah, I mean, I'm sure I'm going to get one soon and start tinkering on the weekends because now I'm very nostalgic about my 11, 10, 12 college days.
Yeah.
All right, if that's all, guys, we can then call it a day, and then we'll be here again tomorrow at 4 o'clock. We have a bunch of sessions scheduled for tomorrow. It'll be the same schedule. We'll start at 4 and end at 7. So thanks everyone. Thanks Amit, Akshay, Anul, and Jitin for sparing some time to talk to us today. Right.